Within a short 72 hours of September, two seemingly unrelated events awakened a question we have long avoided. The deep sea off the Kamchatka Peninsula shook with a magnitude 7.8 earthquake, aftershocks spreading like drumbeats beneath the Pacific. 3 days earlier, Earth had been swept by a strong geomagnetic storm, an invisible wave brushing against the ionosphere and power lines like wind across the strings of a harp. Between these two pulses of Earth and sky, an interstellar visitor is entering the stage. 3I Atlas, a body from beyond the solar system, flared unusually early with a surrounding atmosphere so wide it forces us to rethink the meaning of the word normal. Tonight, we pose a simple question that is not at all easy to answer. Is 3I Atlas triggering earthquakes? And if so, how? The interstellar energy harvesting hypothesis proposes that such an object might collect plasma energy from the solar wind and then alter the natural currents in near-Earth space. The issue is, how much energy is enough to touch faults already loaded with stress? How much is coincidence and how much is mechanism? If you are curious about where science touches the boundary of the unknown, stay with us. Subscribe, turn on the bell, and join us as we peel back each layer of the story. When the sky changes, we too will change the way we listen to the Earth's voice. Part 1. The earthquake. Question. Coincidence or hidden trigger. We begin with the most obvious thing, which is also the easiest to overlook. Large earthquakes are usually followed by long strings of aftershocks. When a fault slips strongly, the energy does not vanish but is redistributed, creating areas that bear more stress and others that are temporarily relieved. The timing pattern of aftershocks often follows a surprisingly simple law. Frequency decreases with time, fast at first, and then more slowly, like a great bell that has just rung and lets its sound fade into the air. This is called the modified Amori law. The magnitudes of the tremors follow another law. Statistics show that large quakes are much rarer than small ones, according to the Gutenberg-Richter relationship. These two mathematical compasses are the foundation that helps seismologists distinguish what is ordinary from what makes them raise an eyebrow. The 8.8 magnitude quake off Kamchatka was a colossal event for the tectonic system of the Pacific Rim. Such an event, with a rupture zone hundreds of kilometers long, can change the stress map over a vast region. Some places tighten, others relax, and other boundaries suddenly become more sensitive to the smallest perturbations. When a 7.8 magnitude quake then struck in the same system, the natural first reaction of specialists was to file it as part of the aftershock sequence. Still within that region, still within a not too unusual time frame, still consistent with the probabilities suggested by statistical models. Coulomb's stress transfer theory neatly explains why adjacent faults can be pushed to the slipping threshold right after a massive initial rupture. But if we widen the time frame slightly, we see that in the days before the ground shook, the sky had its own pulse. A geomagnetic storm strong enough to light auroras farther south than usual, strong enough to disturb radio systems, strong enough to make magnetometer charts oscillate up and down to the beat of space weather. This coincidence, on its own, is still just a coincidence. The Earth always has earthquakes. The Sun always has activity cycles. These two flows always run in parallel, and any crossing point between them may simply be the result of statistical crowding. The cautious stance is not to rush to connect them with a causal thread. Yet science stories are often fascinating precisely because some dare to look for that thread, if only to prove it does not exist. Stepping into their shoes, we ask differently. If some mechanism allows electromagnetic variations in space to slide down into Earth's crust, what path would they take? Which circuits could bring them to where faults teeter at the edge of slip? During geomagnetic storms, induced currents in the crust and mantle can increase. These currents, called geomagnetically induced currents, tend to follow more conductive structures, like water-rich sedimentary basins or mineralized belts. At the local scale, they could alter pore pressure in rocks, slightly shifting frictional conditions on fault surfaces. For a system perched right at the brink, a tiny change may be enough. The key question is amplitude and timing. In an aftershock sequence following a megaquake, the probability of another large event in the first weeks is already high. If an external stimulus does play a role, it can only act as a clock setter, bringing forward an event that was already on its way, rather than creating one out of nothing. This is the view where the cautious and the bold can meet at the same table. One side notes that the mechanical energy of a great quake far surpasses any ordinary electromagnetic disturbance. The other replies that energy need not be matched. Timing alone can matter. Of course, not every coincidence deserves weight. Serious models require more than a few striking examples. They need long time series, independent comparisons, and statistical tests that exclude selection effects. And when such stringent demands are placed, most research so far has failed to break down the wall of skepticism in seismology. But the line between no evidence yet and impossible is two very different boundaries. In the space between them, new hypotheses are allowed to breathe, provided they accept being tested. At this point, 3i Atlas enters not as an exclamation mark, but as an open question. A rare interstellar object showing unusually early activity is generating a gigantic plasma interaction zone with the solar wind. If there is a time when the link between geomagnetic storms and earthquakes will be tested most severely, it is when such a foreign plasma structure passes through the inner solar system, not because it promises some mystical push, but because it may highlight tiny mechanisms otherwise hidden in ordinary days. We do not need an invisible hand to shove whole tectonic plates, only a gentle tap at just the right table edge. But before going further, we must set a clear standard for the original question. What counts as triggering? If an electromagnetic disturbance from space can change the probability of a fault rupturing within a well-defined time window, with a measurable intensity threshold, and with a repeatable mechanism, then we can consider the word triggering fairly. Otherwise, if everything is just stories told after the fact, if every link is woven together by selective memory, then this is a lesson in bias, not in geophysics. Thus, the rest of our journey will follow two parallel tracks. One seismological, recalling the fundamental laws that govern aftershock sequences, recalling how stress is transferred in fault networks. One space-oriented, tracing how energy moves in plasma, how magnetic fields bind and release charged particles, and how currents generated in the upper atmosphere can reach into rock. Where these tracks cross may be the place where 3i Atlas leaves a trace we can measure, not by feeling, but by numbers. Aftershock sequences often follow the modified Omori law, meaning the number of aftershocks decreases with time, fast at first, then more slowly. Earthquake magnitudes usually follow the Gutenberg-Richter relationship, showing large events are exponentially rarer. Coulomb's stress transfer explains how a main shock can increase or decrease slip probabilities on nearby faults. Meanwhile, geomagnetic storms can induce currents in Earth's crust, called geomagnetically induced currents, though their effect on fault slip remains debated. I do not believe in a hidden switch that can turn earthquakes on and off at will, but I do believe in the power of small signals at the right time. If 3i Atlas helps us see more clearly a fragile mechanism linking space and the Earth's interior, then its value lies not in spreading fear, but in enabling us to measure more precisely what once could only be told as intuition. If the true question is whether 3i Atlas is triggering earthquakes, then we need a measurement framework strong enough to separate coincidence from a meaningful link. In other words, instead of stories, we need a natural experiment redesigned through data. The starting point is the monitoring system of near-Earth space. Space physicists use many indices to describe space weather conditions. The KP index summarizes global magnetic disturbance over 3-hour periods. DST records equatorial geomagnetic depression due to the ring current. AE reflects auroral electrojet activity, where strong currents flow into and out of the upper atmosphere. Outside the magnetosphere, The speed, density, and direction of the solar wind are measured nearly continuously by monitors at the L1 point. Those dry numbers are the heartbeat of the plasma environment Earth swims in. On the Earth side, we have our own pulses. The Global Earthquake Catalogue lists the location, time, magnitude, and depth of every recorded event. For known fault zones, stress transfer models can estimate which areas see increased or decreased slip probability after a rupture. If we treat earthquakes as a non-stationary point process, we can use tools like self-exciting Hawkes models to separate endogenous aftershock propagation from exogenous triggers. If a space signal acts as a spark, we would expect the baseline intensity of earthquakes to rise in a narrow window after strong disturbances, even after controlling for aftershock effects. The analysis design can proceed step by step. First, define space events. For example, set Kp greater than or equal to 6 as the threshold for strong storms, or choose intervals where solar wind speed exceeds 600 kilometers per second with abnormally low density, a signature of high-speed streams from coronal holes. Next, set sensitive time windows. Some hypotheses suggest effects could appear quickly, within 24 to 72 hours, when induced currents more easily reach stressed faults. Then compare the number and total energy of earthquakes observed in those windows with random control windows of equal length, same region, same aftershock background. To avoid being dazzled by a few impressive cases, we must repeat across regions, years, and different criteria, applying multiple hypothesis corrections. Even if we see a statistical signal, the question of mechanism remains. What can an induced current change at the scale of rock and faults? When electric fields vary, charged particles in pore water move, altering local pore pressure. Effective friction on fault surfaces depends on this pressure. If friction decreases slightly in a segment already close to slip, a tiny rupture can cascade into an uncontrolled slip if the surrounding stress network is ready to transmit it. This is the image of an extremely sensitive machine, thousands of nodes interacting, where sometimes one tiny nudge in the right spot sets off a cascade. Yet the history of earthquake precursor studies is full of humbling lessons. Many groups once claimed to observe ionospheric anomalies before major quakes, measured by total electron content. Some reported tiny geomagnetic variations before big events. But with broader datasets, many signals vanished or turned out mixed with other natural cycles like space weather, seasonal changes, or measurement noise. The lesson is that every model must control for aftershock sequences, seasonal cycles, station coverage, and sampling bias. Otherwise, we rewrite the sky according to our wishes. Where 3i Atlas makes the story noteworthy is not because it adds mystery, but because it creates a unique stress test. A coma rich in easily ionized gases expands the interaction volume with the solar wind, potentially producing an interference zone where the direction and magnitude of magnetic fields ripple unusually as the object nears perihelion. If electromagnetic effects on Earth exist, then the weeks when 3i Atlas is closest may be the best chance to detect them, especially with the Sun already in an active cycle. Experimental design for this phase could include control pairs from equivalent calendar days in past cycles without similar interstellar visitors to see whether this year's pattern stands out. American audiences may ask a very practical question: what does this mean for daily life? The straightforward answer is that even if the effect is real, your personal risk is still mainly determined by your local seismic hazard map. A home in California or Alaska lives with earthquakes under the rules of its faults, its soil, and its building codes. What changes, if the hypothesis is confirmed, would be how we schedule maintenance for critical infrastructure, allocate emergency resources during higher risk windows, and design standards for electromagnetic resilience in power grids, communications, and satellites. It could also help the insurance industry assess risk more dynamically by combining space and seismic data. One real difficulty is avoiding the trap of chasing elegant patterns. Strong geomagnetic storms are relatively rare. Large earthquakes are also rare. When two rare things meet, the story naturally feels compelling, but compelling is not enough. We must force the data to run against our desires by setting tests that a false hypothesis will fail. A powerful method is pre-registering predictions. Set criteria before observation days, announce the test window in advance, lock in the strength threshold, and only then open the data. If across many rounds the signal still recurs, skepticism may gradually give way to cautious consensus. In the meantime, the right approach is to hold two lenses at once. The first lens reminds us that most earthquakes can be explained by rock mechanics and plate dynamics. The second lens reminds us that Earth is not isolated from space. Magnetic fields, currents, and plasma enveloping our planet are part of a story much older and larger than human lifespans. If there is a fine thread connecting them, our job is not to weave but to untangle, to see which threads carry weight and which are just reflections of light. Analyzing the link between space weather and earthquakes requires combining KP, DST, AE indices, solar wind, and interplanetary magnetic field data with the global earthquake catalogue. Statistical tools like Hawk's models help separate endogenous aftershock propagation from exogenous triggers. Pre-registered criteria and testing windows reduce sampling bias. Even if correlation is found, a plausible physical mechanism is needed, such as pore pressure change from geomagnetically induced currents. I like challenges that force us to redefine words. Triggering should not mean creating from nothing, but adjusting timing in a system already tense. If one day the data shows that space can nudge Earth's clock hand forward a notch, I would not feel fear. I would feel gratitude, for then we would have another clock to look at, before the rocks speak on their own. Part 2. 3 Atlas. The interstellar energy collector hypothesis. To put the hypothesis of an energy harvesting machine on the table without turning it into fantasy, we must first describe in astrophysical terms what 3 Atlas actually is. This is the third confirmed interstellar visitor to pass through the modern solar system. Unlike native comets that usually awaken only when they penetrate deep enough, 3I Atlas has shown unusually early activity. Even at distances where most icy bodies remain silent, it is surrounded by a faint gas envelope so vast it is astonishing. Spectral data suggest a composition rich in volatile gases, with carbon dioxide playing a prominent role. This compound sublimates more easily than water ice, so even under sparse sunlight it can flip the switch, releasing gas and dust, swelling the coma into an enormous size. But size is not the only oddity. The forward brightening along its direction of motion, what observers call forward scattering, indicates uneven outgassing across its surface. That implies a non-uniform rotation axis and heterogeneous thermal structure. Some areas may be thin layers rich in volatile ices, others may be inert crust. As volatile patches rotate into sunlight, gas plumes jet out in turn, creating asymmetric patterns of brightness. All of this remains within cometary physics. Yet under another lens, those plumes are also tiny thrusts, capable of subtly altering trajectory. A natural body might do this by chance. An artificial body, if it existed, could deliberately optimize itself. Now, let's open the hypothesis. A plasma energy collector is not a motor in the classical sense. It resembles a sail more than a propeller. In interplanetary space, the solar wind is a stream of charged particles flowing day and night. If one deploys a structure that strongly interacts with those particles and their magnetic field, it can harvest both kinetic and electromagnetic energy from the flow. For an active comet, the coma functions as a gigantic interaction volume. Each neutral molecule ionized by sunlight instantly becomes a particle guided by magnetic fields, forming the ion tail. The transition zone, where particles are stripped of electrons, is where solar wind energy is transferred into surrounding material as heat, radiation, and plasma oscillations. If a well-organized magnetic field exists near the nucleus, theory allows it to channel particle flows along curved paths, like invisible waveguides. Within those channels, potential differences can become currents. Imagine a hydroelectric generator, with charged particles as water, magnetic field lines as tunnels, and the interaction zone as turbines where energy concentrates. For a natural comet, most of that energy dissipates into space as waves and radiation, while the body itself gains only slight heating and micro-impulses. But if magnetic control exists, magnetohydrodynamic theory permits raising energy harvesting efficiency. That is the conceptual framework behind the phrase plasma energy collector. You might ask immediately, what is such a structure for? From the perspective of a civilization needing to travel far and long, 3 clear benefits appear. First, energy for observation, data processing, and system preservation during long journeys. Second, micro-navigation without carrying large amounts of fuel, by turning plasma interaction into small but steady thrust. Third, environmental probing, collecting flow characteristics around stars during multiple phases of activity. Each passage through a stellar system could both recharge and survey the system's natural electric circuit. This picture may sound bold, but its value lies not in sensationalism. It forces us to write testable predictions. If a giant natural comet is large enough to act as a plasma sail, we can still look for objective signs. Ratios between coma size and energy input-output in the interaction zone, the symmetry of the ion tail as the solar wind shifts, the presence of wave oscillations in radio data as the object crossing magnetic field gradients. If the energy collector hypothesis has substance, we should expect evidence of deliberate modulation of particle flows, not merely random outbursts from sunlight. A common counterpoint is efficiency. At Earth's orbit, the solar wind is not a rich energy stream compared to mechanical sources within planets. The available power per area is low, but the aim here is not to power a city. The aim is a steady, continuous flow over months and years. If the interaction area is large enough, accumulated energy becomes significant. And for an object not supporting a biosphere, only maintaining instruments and small thrust, the threshold is far below our terrestrial intuitions. Unlike Oumuamua, which stirred debate with its unexplained non-gravitational acceleration, 3I Atlas behaves more like a comet. It carries gas and dust, venting material as it warms, producing visible tails. That places the hypothesis into a cautious mode. If there is a technological aspect, it must be hidden within natural behavior. It could be the exploitation of cometary mechanisms, enhancing efficiency without leaving anomalous signatures. From a research standpoint, this is the hardest scenario, an object behaving naturally, yet with micro-adjustments serving its purpose. There is another aspect rarely mentioned. Energy harvesting need not serve only the object's benefit. It could also be part of an experiment in environmental response, injecting energy into plasma circuits and observing how a stellar system reacts. Laboratories do this inside clean rooms and vacuum chambers. The cosmos may do the same at the stellar system scale. If so, sensitive regions, magnetic poles, ground electrical grids, and, at a razor's edge, stressed faults could be accidental sensors of such an experiment. Keeping both feet on the ground, let's recall a principle. No harvesting mechanism can invent an earthquake where stress is absent. The most an energy nudge can do is advance the timing of a rupture. That does not lessen our responsibility for building codes, disaster education, and infrastructure monitoring. If another cosmic clock exists, it only gives us another data channel for probabilistic warning models. That is how a bold hypothesis can be brought back into daily life, not to inspire fear, but to improve preparedness. 3I Atlas is an interstellar body showing early activity at a great distance, with an enormous coma driven by volatile sublimation such as carbon dioxide. Uneven outgassing creates forward scattering brightness patterns. In the solar wind, the coma is where neutral material is ionized, converting flow energy into heat, radiation, and plasma oscillations. The concept of a plasma sail and energy harvesting rests on charged particle magnetic field interactions, potentially forming currents if magnetic structures are organized. This is the theoretical framework testable by observations of tail morphology, radiation spectra, and signs of particle flow modulation. When I imagine 3I Atlas as a machine, I do not borrow magic. I borrow plasma physics and ask, if someone wanted to exploit it, how would they do it? The answer may be, no one. It's all natural. Yet even so, we still learn to read the subtle signals of wind and magnetism in a rare encounter. For me, the greatest value of the hypothesis lies not in conclusions, but in the discipline of turning imagination into measurable tests. The energy collector hypothesis can stand only if we turn it into a set of observable, falsifiable predictions. The best way is to publish a list of expected signatures a plasma sail comet would leave in data, then systematically check them against the times 3I Atlas crosses different magnetic regions of the solar system. In other words, if this is an energy harvesting machine, it will breathe to the rhythm of the solar wind. That breath should appear in sensors. The first signature, ion tail morphology and coma variation as solar wind conditions change rapidly. In a natural comet, the ion tail aligns roughly with the interplanetary magnetic field and wind velocity, with smooth bends as parameters shift gradually. If active modulation exists, we would expect small systematic deviations between tail direction and field orientation, repeating when wind strength increases or field structures shift. Such small deviations are hard to see by eye, but measurable through morphology tracking algorithms across multi-wavelength image sequences, cross-referenced with ionosphere solar wind data. If deviations appear too frequently or cyclically with the body's rotation, that is worth deep investigation. The second signature, radio and ultraviolet emission spectra from the interaction zone. When charged particles are accelerated and guided through organized magnetic tubes, plasma waves like Langmuir oscillations and cyclotron resonances can leave imprints in low frequencies and in specific ion emission lines. Ground radio observatories and satellites beyond Earth's interference can record small bursts synchronized with solar wind pulses. If 3I Atlas is only passive, emission spectra will mainly mirror external conditions. If there is modulation, repeating motifs unexplained by mere wind variation may appear. The third signature, slow correlation between the interaction area and the rotation cycle. An effective plasma sail could optimize the relative orientation between a hypothetical magnetic axis and the wind to maximize energy capture. If so, each rotation might produce phase-linked variation, leaving a faint but steady rhythm in specific spectral brightness or ion tail strength. Time-resolved spectroscopy and rotational modeling will be key. A stable rhythm beyond external variability suggests an internal setup rather than pure randomness. To hunt these signatures, we need a synchronized instrument network. At the solar frontier, monitoring stations like DS, COVR and ACE at L1, plus Parker Solar Probe and Solar Orbiter near the source, provide input dashboards. In Earth orbit, ultraviolet and X-ray satellites track radiation. On the ground, optical and radio telescopes distributed across longitudes build continuous records. Added to these, the global magnetometer network captures local geomagnetic responses if notable synchronous oscillations occur. The core is timestamp synchronization across all data sources, since we seek subtle causal links, not isolated anomalies. A hard but crucial part is building solid baseline models. Magnetohydrodynamic simulations predict tail morphology and interaction regions of a comet under varying wind without active modulation. Such models are computationally heavy but necessary as benchmarks. Any mismatch between observations and simulations must be tested. Is it due to input errors, physical simplifications, or something beyond the natural framework. Without baselines, anomaly risk is an illusion of crude modeling. At the quantitative level, we can estimate the power a giant coma can interact with. Solar wind energy flux at Earth's orbit is low compared to terrestrial mechanical sources, but multiplied by the effective cross-section of a coma, hundreds of thousands of kilometers wide, accumulated energy is non-trivial, especially over weeks. This is where intuition misleads us. We compare to power grids or engines, but here the mission is sustaining instruments and light navigation modest needs for a body without a biosphere. Yet even if cumulative power is meaningful, linking it to earthquakes requires a firm mechanism bridge. We are not speaking of a beam aimed at a fault, we are speaking of small shifts in the amplitude of natural currents and fields around the Earth, leading to minor variations in induced currents through the crust and mantle. The effect, if real, would be a slight increase in triggering probability where faults are already primed. Observational tests should thus focus on regions with strong aftershock sequences or clear stress buildup, where a tiny tap can be amplified. The testing framework must also account for common confounders. Coronal mass ejections create storms with dynamics distinct from high-speed coronal hole streams. Their effects on geospace differ in timing patterns. If 3I's Atlas's plasma cell hypothesis is partly correct, we might expect clearer effects during prolonged high-speed streams, favorable for steady interaction, rather than during short, violent bursts of eruptions. Separating these in analysis will clarify or refute a branch of the hypothesis. A legitimate concern is how to distinguish a very active comet from a cleverly hidden device. The short answer: statistics and pre-registered predictions. If we only narrate after events, any story can be made convincing. But if before 3I Atlas reaches perihelion, we publish criteria, a checklist of observational signatures counted as pass or fail, and analysis methods, the results will carry weight, whether confirming or denying. Science may lose to stories in drama, but it wins in discipline, and that discipline keeps us from getting lost. In the end, whichever way the story unfolds, monitoring 3I's Atlas as a natural experiment still yields immediate benefit. It forces multi-wavelength, multidisciplinary networks to coordinate, improves algorithms and processing pipelines, accelerates magnetohydrodynamic modeling applied to comets, educates the public about some plasma magnetism Earth connections, and grants us a rare chance to test electromagnetic interaction ideas in a defined time frame, rather than scattered coincidences in history. The observational signature set for the energy harvesting hypothesis includes systematic ion tail deviations from field orientation, repeating motifs in radio/UV spectra, suggesting organized plasma waves, and rotation-linked variability rhythms. Instrument networks must synchronize data between L1 monitors, solar probes, satellites, and ground stations. Magnetohydrodynamic modeling provides baselines. In seismic risk analysis, focusing on stressed regions boosts sensitivity if triggering effects exist. I do not need 3I Atlas to be a machine for this journey to be worthwhile. If it is merely an unusual comet, we still push the limits of observation and modeling. If it leaves intriguing hints, we gain a bigger question to pursue. If it leaves silence, that too is an answer. In all three scenarios, the most important thing is that we turned curiosity into measurable, falsifiable, repeatable tests. Part 3. The physics of plasma harvesting. To understand why the idea of harvesting energy from the solar wind is not a fantasy, we must step into the classroom of plasma, the dominant state of matter in the universe. Plasma is a gas that is partially or fully ionized, meaning it contains free charged particles such as electrons and ions. Unlike neutral gas, plasma obeys two stricter masters: electric fields and magnetic fields. When an electric field changes, electrons respond almost instantly, triggering chain reactions. In the presence of a magnetic field, charged particles do not fly straight, but spiral around field lines, tracing helical paths with characteristic frequencies. From these simple rules, a forest of phenomena emerges: plasma waves, instabilities, magnetic reconnection, boundary layers, shocks, and immense currents linking regions of space. The solar wind is plasma streaming out of the corona, typically a few hundred to 700 kilometers per second at Earth's orbit. It carries not only kinetic energy, but also a weak yet persistent magnetic field, the interplanetary magnetic field, wound into a spiral by the sun's rotation, the Parker spiral. When the wind collides with Earth's magnetosphere, two magnetic flows crash, creating a complex system of reconnection. On the night side, the magnetosphere stretches into a thin tail, where energy is compressed and then released in plasma bursts that light up the aurora. An object with a coma as vast as 3I Atlas, entering this flow, is not just a stone crossing a stream. It is like a thick sponge soaking water, except the water here is charged particles and magnetic energy. On the sunward side, the wind is partly blocked, forming a magneto-hydrodynamic shock, where part of the kinetic energy turns into heat and waves. Deeper lies the boundary layer, where solar wind plasma mixes with freshly ionized cometary gas. Here, electrons are accelerated, Langmuir waves arise, cyclotron resonances appear, and freshly born ions are swept away to form a straight ion tail. Harvesting energy from this environment does not need a spinning turbine. It requires electromagnetic potential differences and pathways for current. Simple metal electrodes would corrode and fail in space, but plasma can serve as its own conductor. In natural plasma waveguides, potential differences arise along magnetic field lines whenever particles are accelerated. If a structured magnetic field surrounds the nucleus, it could act like a valve, routing flows through regions more capable of generating current. Imagine field lines as invisible highways, with resonant mechanisms as toll stations where some of the flow's energy is skimmed off. But where would such a magnetic structure come from? A natural comet does not carry a superconducting magnet. Yet, induced currents can create local fields. As plasma flows around a conductive body, loops of current arise, just as eddies form around a rock in a river. If the nucleus contains conductive minerals, if outgassing geometry channels charged flows, localized fields may appear strong enough to organize plasma on scales of tens to hundreds of kilometers. Not perfect, just sufficient to raise capture efficiency compared to a fully free cloud. When a neutral particle is ionized, it changes citizenship and immediately comes under magnetic rule. This process is called ion pickup. The newborn ion's initial velocity matches the comet, but instantly it is forced into a spiral around field lines, as if tethered to a rotating pole. The energy for that tether comes from the wind. In other words, the solar wind does the work of converting neutral matter into charged particles that obey its laws. That work can be gathered into a current if there is a circuit. Without a circuit, energy disperses. With one, energy becomes a flow, and that flow can be used for something, even if only to maintain itself in a feedback loop. A surprising aspect is that efficiency need not be high to matter. In space, the precious resource is not large, instantaneous power, but a steady trickle accumulating over months and years. If 3I Atlas's coma spans hundreds of thousands of kilometers, its effective cross-section is staggering. Each neutral particle ionized and carried away represents solar wind energy converted. Most is lost, but even a small fraction could sustain a measurement system. Another layer of physics strengthens the plasma sail idea. Magnetic fields do not just guide particles, they trap energy within structures. Boundary layers, where field direction changes suddenly, are prime sites for energy conversion. If an object can place itself at the right angle to the wind and field, it can optimize interaction. Orientation, in other words, boosts harvesting power per unit area. For a natural comet, this occurs semi-randomly as it spins and orbits. For a device with intent, optimization could be systematic, leaving rhythmic signatures as already discussed. At this point, a fair question arises. How does this mechanism connect to Earth? The link lies in plasma as a system of giant circuits. Earth's magnetosphere is an energy generator, stretched and released by the solar wind like a bowstring. Currents flow into and out of the high-latitude ionosphere, closing circuits through the global electric field. Any persistent upstream change in wind and field can shift the balance. An object like 3I Atlas, by distorting the flow, could leave micro-ripples on the plasma lake Earth floats upon. From these ripples, induced currents in the crust might change in ways felt only by fault systems already at the edge of slip. We are not claiming anything. We are building a physics bridge from solar wind to a giant coma's capacity to harvest energy, and from there to small variations in Earth's electromagnetic circuit. If the bridge holds, we step further with measurements. If it collapses at some parameter or unrealistic assumption, we rebuild. The most valuable thing is that each span of the bridge is a testable model, with prediction data that can be refuted. Plasma is an ionized gas governed by electric and magnetic fields. The solar wind is plasma carrying kinetic energy and the interplanetary magnetic field. When it meets a large cometary coma, shocks, boundary layers, and ion tails form. Ion pickup transfers wind energy into newborn charged particles. The energy harvesting concept rests on electromagnetic potential differences and the ability to channel particle flows through organized magnetic structures. Turning some flow energy into measurable current or radiation, I prefer to see the universe as a giant electric circuit rather than an empty desert. That view requires no magic, only patience to follow the invisible threads between particles and fields. If 3I Atlas is only a buoy on the plasma river, it still teaches us how to read the flow. If it is a clever paddle, then each ripple it creates becomes a new page to read. When an idea begins to take shape, the next step is to lay numbers on the table, not decimal precision, but order of magnitude checks. At Earth's orbit, solar wind has a density of a few protons per cubic centimeter and speeds of 400 to 700 kilometers per second. The kinetic energy per unit volume is small by Earth standards, but the flow never ceases, and continuity gives it meaning. If 3I Atlas's coma has a radius of several 100,000 kilometers, the effective cross-section is immense. Each neutral ionized and entrained represents a unit of transferred energy. Even if only a tiny fraction is captured by organized fields and flows, cumulative weeks of interaction could sustain instruments and navigation. But efficiency is the tough question. In a natural comet, most pickup ion energy is scattered or radiated, turning into heat at the boundary, into plasma waves, ultraviolet, and soft X-rays. To turn this into a usable current requires two conditions. First, some organized local magnetic field, even on the 100-kilometer scales, forms channels where potential differences arise. Second, geometric alignment between the rotation axis, a hypothetical magnetic axis, and wind direction, such that interaction intensity varies cyclically rather than randomly. Even without artifice, a comet rich in volatiles with special outgassing geometry might achieve natural efficiency higher than average. Here, the boundary between natural optimization and engineered design blurs. What connects this imagined machine to Earth? Return to the planetary circuit. Earth's magnetosphere is a generator stretched and released by the solar wind, channeling energy from the day side to the tail and back through the poles. Long-lasting upstream changes such as high-speed streams with low density push the system into a high-energy baseline. If 3I Atlas, with its vast interaction volume, distorts fields or induces organized turbulence on a local interplanetary scale, micro-ripples could resonate with Earth's natural frequencies. At the surface, this appears as small variations in geomagnetism and electric fields, altering induced currents in conductors. Normally, this is background noise. At a fault poised at the threshold, it could be a timely tap. Yet every hypothesis must face practical constraints. First, energy ratio. The mechanical energy released in a great quake far exceeds any space disturbance within the same time window. Thus, any trigger from above can only act as a clock, not as fuel. Second, fault sensitivity. Not all faults react equally to pore pressure or electric field changes. Rock composition, water saturation, temperature, and surface roughness all define amplification factors. Third, timing patterns. If the mechanism is real, it must leave consistent delays between electromagnetic disturbances and rising quake probability, not just scattered coincidences. How to test these constraints? One strategy is to target intervals when 3E Atlas traverses regions of different wind and field characteristics, predicting what signatures should appear in geomagnetic and ground electric data, then tracking earthquake probabilities in regions with active aftershock sequences. For example, during prolonged high-speed streams with low density as solar wind vacuum sensor networks can watch for long, low-frequency geomagnetic variations at mid-latitude stations. The question then is not, will a large quake occur, but does the timing distribution of aftershocks statistically deviate from baseline self-exciting models? Another strategy is reverse observation. When 3I Atlas moves away and solar wind conditions return to normal, any linked signals should shut off in phase. This simple but powerful check reduces false correlation. If effects only appear when 3 conditions overlap, comet nearby, sun in high energy phase, faults under stress, then spurious coincidence is less likely. Still not proof of causality, but enough to bring the hypothesis into serious observational consideration. We must not forget inherent confounders. Coronal mass ejections deliver short, violent punches, often causing high-level geomagnetic storms. High-speed streams, by contrast, carry long, steady rhythms. If 3I Atlas truly optimizes in long rhythms, predicted signatures differ from CME-dominated environments. Separating the two in analysis is key. Geometry between the Sun, Earth, 3I Atlas, and solar wind may also amplify effects in one hemisphere but not the other, requiring ground stations spread across latitudes and longitudes. At the experimental design level, the most important element is falsifiability. Before an observation window, state clearly if L, M, N do not appear in cometary radio spectra when wind shifts, if delta is absent in mid-latitude geomagnetic data within 36 hours of upstream disturbance, if aftershock timing distributions do not deviate within 72 hours, then hypothesis 1 is rejected. Next time, hypothesis 2 is adjusted or discarded. This cycle of elimination turns ideas into science or pushes them back into suggestion. An overlooked angle is sympathy windows. In our technological society, even without seismic impact, small fluctuations in the global electromagnetic circuit can touch power grids, GPS, aviation, radio systems, at levels subtle but operationally meaningful. If we predict phases when persistent noise rises, critical infrastructure could go on mild alert, much as aviation reroutes around solar weather. The final reminder is humility. Plasma physics of interplanetary space and fault friction mechanics are both complex domains where elegant models may clash with messy data. The energy harvesting hypothesis builds a bridge between them, but the bridge must withstand storms from both sides. If it breaks, we know why and where. If it holds for a few seasons, we gain confidence to add sensors, recruit colleagues, and write a small but solid chapter. Order of magnitude estimates show that although solar wind energy density is low, a vast coma can accumulate energy over time. Efficiency depends on local magnetic organization and geometric orientation. Impact on Earth, if any, comes through small geomagnetic and electric variations affecting induced currents. Tests need pre-registered criteria, CME versus high-speed stream separation, multi-station monitoring, and statistical aftershock distribution analysis. I like honest numbers. They promise no miracles, only whether an idea deserves pursuit. If 3I Atlas leaves no anomalies, we still gain a grand test of our observational power. If a few signatures match predictions, the story will not need sensationalism. It will quietly, persistently enter textbooks. Part 4. From Space to Earth, the Energy Pathway, to connect the story of a distant plasma object with the ground shaking beneath our feet. The prerequisite is a roadmap of energy flow, from the solar wind to the magnetosphere, from the magnetosphere to the ionosphere, from the ionosphere down into conductive rock, and finally to faults under stress. That path is not a straight wire, but a whole network of currents and potentials, where each node has a life of its own, yet it remains a network. It allows small variations upstream to shift states downstream, especially when the system is perched at a threshold. Begin at the upstream boundary. The solar wind carries the interplanetary magnetic field. When the orientation of this field, usually denoted BZ, turns southward, it collides with Earth's magnetic field, generated by the spinning iron core. On the day side of the magnetosphere, two opposing field systems can reconnect, like two rubber bands pulled together, suddenly swapping partners. That reconnection opens doors for plasma and energy to pour inward. On the night side, the magnetotail stretches like a wind-filled sail. Energy stored in the tail eventually releases as plasma bursts, sending energy packets back along field lines to the magnetic poles. There, field-aligned currents drop into the ionosphere like anchors, igniting auroras and redistributing atmospheric potentials. The ionosphere is where space first touches our dense atmosphere. It conducts differently along and across field lines. Under the influence of electric fields from above, charged particles in the ionosphere drift in organized ways, creating a skyborne current system. But this current does not stand alone. It closes its circuit through currents that flowing on the surface and into the ground, called geomagnetically induced currents. On quiet days, these are weak and scattered. During disturbed days, they strengthen, following paths of least resistance. Water-saturated sedimentary basins, sulfide ore belts, graphite-rich metamorphic zones, or crustal boundaries with strong resistivity contrasts. A region's geoelectric map, if well measured, is almost a traffic map for these currents. Why do geomagnetically induced currents matter? Because rock, though strong, is an electrochemical medium. When current passes through porous media containing electrolytes, electrokinetic effects occur, and water migrates slightly along the field. These small displacements can change pore pressure in microfractures. In fault mechanics, pore pressure is the dial for effective friction. Higher pressure reduces friction, making slip easier. Lower pressure locks it tighter. Even a few % change can be enough if the fault system is near instability. Laboratory-scale experiments in electrochemomechanics already show this linkage. Piezoelectric, electrochemical, and electroosmotic effects. At a natural scale, the challenge is amplitude and timing. The picture sharpens when placed in a real region. Imagine a subduction zone offshore, where kilometers of sediment are compressed and fluid-rich. Above the main thrust lie conductive lenses of salty water or mineralized rock. During a prolonged geomagnetic storm, ionospheric electric fields shift slowly. Induced currents pump these lenses gently. If at a fault patch, local pore pressure rises just enough to lower friction, a microslip occurs. If that microslip strikes the lock keystone of the fault network, it can grow into a major event. Not every pump hits the mark, but systems at the edge are sensitive to small taps. The link to 3I Atlas lies in the upstream tier of this picture. A massive coma placed in the windfield flow can introduce phase shifts, harmonic imperfections in the interplanetary magnetic field locally, persisting longer than usual. It need not exceed maximum storm levels. What matters is persistence and structure, so the magnetosphere is drummed longer at certain frequencies. If those frequencies align with resonant bands of the magnetosphere and ionosphere, they more effectively convert into electric field variations overhead. From there, Earth's natural conductive network hears a deep hum instead of a thunderclap. At thresholds, a hum can be more effective than thunder. We must also note spatial selection effects. The magnetosphere is asymmetric by day and night and by season. The geometry between wind direction, Earth's axis, and the interplanetary field shifts rhythmically. So if 3I Atlas distorts wind flows, effects may favor one hemisphere, one latitude band, or certain local times. This is good for testing. Structured signatures are easier to distinguish from randomness. If ground geomagnetic and seismic data show systematic phase shifts tied to reasonable time-space windows, we can step forward. If not, the hypothesis must retreat. Another bridge from electric fields to rock mechanics is the rate and state friction theory. In this framework, a fault surface does not have a fixed friction coefficient. It remembers its slip history. A small but sustained stimulus can age or youthen the surface mechanically, altering how it responds to stress. Meaning, an electric field variation lasting hours may matter differently than a short electromagnetic jolt. When proposing triggers, we must specify which kind of stimulus we expect to matter and why. From the practical perspective of a US audience, this is where science meets daily life. Northern state power grids have a history of geomagnetic currents during strong storms. Oil and gas pipelines spanning north-south may see corrosion rates shift with space weather phases. Navigation systems relying on satellites are disturbed when the ionosphere varies. If we are heading into a phase of longer-lasting electromagnetic variability, infrastructure could benefit immediately from better forecasts and maintenance scheduling even before earthquake questions are answered. Still, we must underline skepticism. This energy pathway has many closed doors. If any door is shut, upstream disturbances stop there. The ionosphere may not respond as expected. Conductive pathways may not connect to faults, or faults may be too far from threshold. Then every knock falls into silence. Science advances by finding the specific spans where doors are ajar, not by assuming they all are. The energy path from space to ground includes steps. Solar wind and interplanetary field reconnect with Earth's field. Energy flows into the magnetotail and down poles along field-aligned currents. Ionospheric potentials redistribute, energizing overhead currents. Induce ground currents close circuits through local conductive structures, potentially altering pore pressures and effective fault friction. Effects may be stronger under long-duration, resonant excitations. For me, this vision is convincing not because it is exotic, but because it restores Earth to its place in a stellar energy network. We are not outside the plasma wind, we float on it. If a visitor can ripple the lake's surface, our duty is to measure honestly and decide which shorelines to reinforce. A roadmap only matters if it leads to specific measurements. So, where do we measure, what do we measure, and in what sequence? To test the energy path from space to fault. For American audiences and infrastructure, the feasible approach is a tiered observation protocol. From space to ground, focused on 3 sensitive regions. The US, West Coast, with Cascadia subduction and San Andreas fault. Alaska with its active plate boundaries. And the central US with the New Madrid system, historically capable of great quakes though infrequent. The upstream tier begins with solar wind and interplanetary magnetic field data. Primary sources are L1 satellites, giving speed, density, plasma temperature, and magnetic vectors. When high-speed, low-density streams appear, or BZ stays southward steadily, we mark golden windows of energy transfer into geospace. Simultaneously, we track geometry between Earth and 3 Atlas, relative position, solar wind impact angle, any tail or emission spectrum changes, possible signs of organized interaction at the comet. The middle tier is the magnetospheric and ionospheric response. Here, ground magnetometer networks at mid and high latitudes are our eyes. We must look beyond aggregate indices like Kp and watch the frequency spectrum of geomagnetic oscillations. PC5 low-frequency bands reflect long magnetotail waves that can resonate with Earth's modes. The ionosphere is probed through total electron content, via GNSS networks, tracing continent-scale charge distributions. When PC5 bands strengthen for long periods and TEC varies systematically by latitude, upstream energy is flowing down effectively. The near-surface tier is where overhead fields touch ground. In northern states and the Pacific Northwest, long-line electric field sensors and geoelectric monitors can record hour-long drifts. Critical is a 3D resistivity map of the crust to infer favored current pathways. These maps, built with natural source EM soundings, using the very geomagnetic variations we now study, form a neat observational loop. Signals used to map are also explained by the map. The deep tier inside the Earth is the hardest. We cannot put instruments on the main faults, but we can watch indirectly. One strategy is monitoring microseismic clusters and slow slip events as they react sensitively to pore pressure and friction changes. In Cascadia, slow slip episodes have been recorded migrating with their own rhythm. If, during an energy transfer window, that rhythm shifts systematically, it is a worthy clue. In California, San Andreas is dense with seismic and GPS arrays. Subtle changes in creep rate on partially locked segments may appear over weeks under slow forcing. Most crucial is linking tiers under pre-registered protocols. Before 3 IATLAS's perihelion window define clear thresholds. PC5 energy, increase above baseline. TEC, spatial amplitude. Ground electric field exceeding median by standard deviations for how long, and seismic responses diverging from aftershock models. These thresholds differ by region due to geoelectric backgrounds, so each needs its own. The key is committing in advance, so results carry weight, whether positive or negative. The central US deserves mention. New Madrid produced historic early 19th century quakes. Today, its station coverage is sparse, and crustal conductivity is complex, mixing ancient cratons and basins. This implies 2 things. Induced currents may concentrate unpredictably at resistivity contrasts, and signals are hard to read without updated 3D maps. For such regions, a practical strategy is to merge data from grids and pipelines. Infrastructure operators often record abnormal currents during storms. Tying engineering logs to geomagnetic and seismic data forms a rare 3-way window into natural circuits. Another unglamorous but essential point is managing false alarms and misses. In a long energy transfer window, more aftershocks in an active zone may simply be background. Conversely, stimulation may occur, but faults fail to respond if too far from the threshold. Each signal must sit in probability language, not certainties. Tools like Hawk's models with exogenous inputs estimate baseline intensity, rises under forcing, combined with multiple hypothesis testing to keep us sober before attractive graphs. Audiences often ask, are there active experiments? In space, realistically, no. We cannot control solar wind or 3i Atlas. On Earth, there are small-scale tests, injecting weak controlled currents via electrodes at shallow faults to probe electrochemomechanical response. Low-amplitude hydraulic tests to gauge amplification before and during space weather phases. Such experiments must follow strict safety, never raising seismic risk. Their goal is to learn mechanisms, not create events. Another practical link is infrastructure alerts. When PC5 bands grow and tech shifts structurally, North American grids can raise sensitivity at transformers, adjust loads, and monitor heating. Aviation can reroute near the poles if needed. Positioning services can enhance ionospheric error filters. These are already procedures for strong storms. The novelty is a finer adaptation to long-phase disturbances, subtle but persistent. Even if the earthquake hypothesis is disproven, infrastructure gains remain. Across all tiers, transparency is key. If a forecast window opens and nothing happens, say so. If EM signals appear without seismic response, explain why that is possible. Public trust is built not on sensational hits, but on long runs of honest reports of both positive and null. This is also the difference between science and story. Science keeps notebooks, story keeps heartbeats. Finally, do not forget the human side in telling the tale. American audiences want to know, should they do anything different day to day? Mostly no, except the basics anyone in Quake country should already have. Emergency kit, family plan, secured furniture. If one day we prove slightly higher risk windows during long phase energy flows, the right message is vigilance, not fear. The best gift a new science can give is more light, not more fuel for fire. Testing the energy pathway requires tiered monitoring. L1 data for solar wind and interplanetary fields, magnetometer networks and GNSS tech for magnetosphere and ionosphere, ground electric field sensors and 3D resistivity maps for induced currents, seismic and GPS arrays for microseisms, slow slip and creep variability. Pre-registered thresholds and windows reduce bias. Signals must be cast in probabilities with statistical models, including exogenous drivers. I believe a new science can grow healthy only if it serves infrastructure and stays honest with data silence. If 3i Atlas passes and every tier shows normality, that is good news. The world is more stable than our imagination. If some tiers hum together, then we learn to listen better and act more calmly. Part 5. Cosmic experiments. Are we the test? There are two ways to look at what is unfolding in near-Earth space. The first, cautious and classical, holds that we are in the middle of a natural experiment with no intent. The sun is at maximum, plasma winds fluctuate, an interstellar visitor with unusual interaction volume happens to pass through, and Earth's magnetosphere responds in its usual language. The second, more controversial and alluring, suggests that some intelligence could be taking advantage of this timing to observe our system in a high-energy state, and that 3i Atlas, natural or fine-tuned, might be a measuring instrument placed in the flow. Either way, the common point is that this is a rare chance to learn, because nature seldom loads so many variables at once. First, be strict with the natural experiment scenario. The cosmos often provides configurations we cannot create ourselves. Long storms, high-speed streams, a powerful comet inside the solar system. What makes this year unusual is the convergence of factors. When variables coincide, we can disentangle their roles by comparing across windows. With 3i Atlas versus without, quiet wind versus strong wind, southward BZ versus not. That is the essence of natural experiments. No intervention, but careful framing of questions so they become answerable. Now the intentional experiment scenario. Assume the extreme. 3 Atlas is an energy harvesting, energy routing system designed to test planetary electromagnetic responses. This assumption matters only if it yields falsifiable predictions. First, an intentional probe would seek stability over chaos. It would aim for recurring interaction patterns tied to its own cycle, regardless of changing wind. If stable rhythms stand out above exogenous variation, that is worth probing. Second, a purposeful experiment would sweep through frequencies to probe responses. This could leave traces in radio spectra or geomagnetic oscillations as systematic frequency shifts rather than random bursts. Third, a real experiment has on-off phases. If 3i Atlas switches modes around perihelion in predicted ways, repeating when outbound, credibility rises. Ethics appear the moment we admit intent. Would a responsible civilization disturb the electromagnetic environment of a biosphere planet? This is why many fall back on the natural scenario. Assume goodwill, avoid imputing intent without proof. Even if intent exists, stimulus levels could be low probing thresholds, not breaking them. As seismologists send tiny signals to image Earth's interior, a cosmic experiment, if real, would aim to stay below harm. The scientific question remains unchanged. Does it leave measurable, repeating signatures? A subtle point is camouflage. A good experiment may deliberately hide as natural, so as not to bias the subject. If technology is advanced enough to leverage comet physics itself, its signatures would blend with the natural background. Then only statistics and pre-registered criteria guide us. We must define ahead of time which patterns count as intentional, e.g., regular frequency sweeps in radio data or small but repeated offsets between ion tail direction and field lines. Everything else, however tempting, stays in the realm of story, not data. How to move the "we are the test" scenario out of storytelling? The direct route is cross-domain validation. If intentional signals exist, they will rarely mark just one layer. They would appear simultaneously in comet spectra, in solar wind data, in geomagnetic oscillations, and perhaps in infrastructure indicators like induced currents. Magnitude need not be large synchrony, and predicted structure are what matter. When independent data streams hum in tune, confidence jumps. When only one sings, we are likely hearing its natural background. Geography also matters. A planetary test would favor regions with conductive structures and stressed faults. Thus, spatial distribution should not be random. In the US, sensitive targets are Cascadia, southern Alaska, and parts of San Andreas. If signals cluster there during defined windows, not spread everywhere, the case strengthens. If they appear broadly, they are more likely ordinary space weather. We must also distinguish triggering from causing. Even in the intense scenario, the most plausible role is shifting timing in systems near failure. That raises the ethical bar and blocks exaggeration. An intentional signal, if it exists, cannot turn safe zones dangerous overnight. It could only nudge probabilities slightly in short windows, and only where risk already resides. Finally, honesty about limits. Much of this is experiment design, not conclusions. After all efforts, data may still show a natural picture. 3I Atlas is simply an active comet, Earth as usual, living under solar rhythms. That is valuable. It sets standards for future interstellar encounters and leaves behind a toolkit of analyses we lacked. If some signatures do appear, we must still ask if natural mechanisms could mimic them before invoking intent. Natural experiments are our framework when direct control is impossible. Compare multiple windows to isolate variables. Intentional scenarios matter only if they yield falsifiable predictions, stable rhythms, systematic frequency sweeps, or on-off patterns across domains. Cross-domain validation comet spectra, solar wind, geomagnetism, induced currents, seismology is the key to trustworthiness. I do not believe in dramatic curtain pulls. I believe in pre-registered criteria and faint repeating traces. If someone is experimenting on us, the best response is to experiment back with rigor, measure, predict, accept error, and refine. If no one is, so much the better, because we will still have sharpened ourselves. That refinement may itself be the lesson the universe always meant to give. If we treat 3I's Atlas's passage as an experiment window, what does a planetary scale protocol look like? No test tubes, no switches. Instead, distributed instruments, pre-registered notebooks, and questions translatable into numbers. The core is expectation control, not hunting for smoking guns of alien intent, but distinguishing natural noise from structured patterns across independent datasets. Step 1. Publish an astrospace calendar. Mark phases with higher potential signals. Perihelion of 3I's Atlas. Alignments that embed its ion tail deeper in the field. Prolong southward BZ and long high-speed streams. For each window, define length, start-end in UTC, and minimal expected baselines per dataset. Publishing ahead enforces discipline. If baselines, e.g., PC5 rise, structured tech variation, are absent, later analysis is downgraded. Step 2. Build a synchrony triangle. Its vertices, comet spectra / morphology, upstream space weather, and magnetosphere / ionosphere response. At the comet, Track ion tail angle and curvature, coma brightness, and any spin-tide repetition. In radio, look for plasma wave emissions. At the upstream, satellites log velocity, density, and magnetic vectors. At Earth, magnetometers record oscillation spectra. GNSS networks measure taxi, and low-orbit satellites track field-aligned currents. Only when all three nod in a defined window comet shifts, wind changes, magnetosphere hums, do we proceed. Step 3. Select target response zones. Not everywhere is equally sensitive. In the US, southern Alaska, Cascadia, and semi-locked San Andreas sections are prime. Criteria: dense seismic arrays, decent 3D resistivity maps, and current post-quake or aftershock activity. For each zone, define 2 response classes: EM, surface electric fields, grid-recorded GICS, and seismic/geodetic, aftershock upticks, shifted, slow slip rhythms, or small creep changes on GPS. Step 4. Respect lag scales. Can both intentional and natural signals obey physics? Solar wind from L1 to Earth takes approximately 1 hour at 400 kilometers per second. Tail energy release to PC5 rise takes tens of minutes to hours. Ionosphere to ground currents, minutes, hours. Ground EM shifts to fault micro response, hours, days. Each dataset must be aligned to its plausible delay. Analyses ignoring lag risk artifacts. Step 5. Run blind controls. Create false windows of equal length during quiet space weather, with a similar seismic background and seasonal context. Analysts at the final stage do not know which ones are real. Repeat in insensitive regions, inland cratons, to see if patterns vanish. If signals appear only in true windows at sensitive zones, the weight increases. If patterns spread, we likely see natural noise. Step 6. Define vote thresholds. Before seismic data are opened, agree on community criteria, e.g., at least 2 of 3 indicators PC5 TEC surface E-field exceed thresholds in expected delays, plus 1 of 3 seismic or geodetic signs, aftershocks, slow slip shifts, creep changes. If unmet, call the window negative, publish openly. If met, tag as candidate, send for independent replication with different baselines. This converts our desire to see patterns into a filterable process. Step 7. Embrace valuable negatives. A null window is not a failure. It sets upper bounds. If effects exist, they lie below detection. Many nulls paint a quantitative portrait of absence, guiding improvements, denser stations, better 3D resistivity, refined tech filtering, or simply waiting for better geometry. Science advances by shrinking the possible space. Now the hard question. If every step yields positives, can we declare we are test subjects? The honest answer is no. What we would have is structured, repeating, synchronous patterns with plausible delays enough to claim an organized mechanism, not enough to claim intent. Next comes searching for rare natural resonances, comet-wind Earth geometries, or unusual twin streams. Only when natural avenues are exhausted does intent return, and even then, only as not excluded. At the human level, this process has a pleasant side effect. It turns cosmic curiosity into infrastructure benefits. Even if seismic links are disproven, better resistivity maps help grids, pipelines, and rail. Sharper tech algorithms improve GPS, denser magnetometers refine storm alerts. Curiosity, when disciplined, pays off even when answers disappoint. A planetary scale experiment is feasible through pre-registered window calendars, synchrony triangles, target zones, lag-respecting analysis, blind controls, and multi-criteria votes. Negative results give upper limits and guide network upgrades. Positive, synchronous, structured signals suggest organized mechanisms, but fall short of proving intent. I believe the beauty of the "we are the test" idea is not in the answer, but in the stance. If someone is measuring us, the most dignified reply is to measure ourselves better. If no one is, even better, for then it is our own refinement that grows. And perhaps refinement itself is what the universe always meant to teach. Part 6. Patterns in history, earthquakes, and cosmic visitors. When a new hypothesis is still forming, our instinct is to look back, asking whether history has ever hinted at something similar. Here, the question is whether there have been eras when major earthquakes, strong space weather, and striking comets all stepped onto the stage nearly at once. We are not seeking definitive answers, only candidate patterns clean enough for today's analytical tools. The crucial discipline is to keep our hands clean, to separate misleading coincidences from structured signals, and standardize records from collective memory. The first principle, dull but vital, is that historical data quality is very uneven. Before the mid-20th century, seismic networks were sparse, dependent on settlements and communication infrastructure. Before satellites, space weather relied on magnetometers at a handful of observatories and sunspot logs. Comet records favored bright, close, obvious objects. Any analysis reaching deeper into the past must be restrained, use few milestones, but solid ones, and accept gaps rather than fill them with imagination. In the 20th and early 21st centuries, some stretches often get cited when people try to link geomagnetic storms, comets, and earthquakes. For example, the early 1960s saw both extremes: powerful storms during a solar maximum, and giant quakes in Chile and Alaska. Yet caution is needed. Those quakes struck subduction zones already primed for massive events, while stormy space weather is simply what happens every 11 years. Parallel series do not imply invisible wires between them. The best lesson is that prolonged storm windows are worth checking against aftershock statistics in active regions, seeing if there are slight biases where models predict. Another often told case is early 2011, when Japan suffered the Tohoku disaster just as the sun was emerging from a long minimum. Here, modern data density matters. Dense seismic networks, GPS deformation tracking, and detailed space weather monitoring. Anyone wanting to test whether long, low-frequency geomagnetic oscillations align with aftershock timing has data to work with. Yet analysis usually hits the same wall. Any effect, if real, is small, buried in strong natural variability, and very sensitive to window choice. Outcomes tend to split, either no stable shift or faint hints that only justify more pre-registered tests. What about comets of the same era? Optical history highlights public spectacles like Halley 1910 or Hale-Bopp in the late 1990s. Both were cultural events more than physical opportunities, since the sun was not at maximum, and their plasma tails mostly served as classroom examples of solar-wind interaction. Through the 3i Atlas lens, what matters is not the brightest comets, but those with asymmetric comae, unusually early activity, or perihelion coinciding with structured, long-lived solar wind phases. Such years are rare, and detailed data are rarer still further back. From recent decades, familiar stories include the 1989 storm that blacked out Quebec and the 2003 Halloween storms that painted auroras far south. But those were infrastructure events, not seismic ones. Any quake connection would lie in subtle shifts in aftershock distributions following giant ruptures. And even then, the next test arises immediately. Do similar patterns appear during strong storms without unusual comets? If so, the comet's role must shrink. A cleaner approach is to pick modern windows with physics-favorable traits: sustained high speed, low-density streams, favorable magnetic polarity, and a large plasma object inside the inner solar system. Then pre-register electromagnetic and seismic markers. If neither layer responds as predicted, the historical link weakens, as science should. If some short windows line up well, more resources can be justified for future encounters. Here lurks the trap of collective memory versus data. Human cultures have long fused comets and quakes in legend, making our brains adept at stitching two images together. Memory is selective, raw data are not. In the US, this has a practical side. If media amplify historical patterns without standardized datasets, the public may leap to emotional conclusions, like imagining quake risks, spikes on nights of bright auroras. The wise safeguard is open data, open methods, and equal weight given to misses as to hits. An intriguing historical clue comes from Cascadia's repeating slow-slip events, cycling over months to years. These do not shake cities, but they breathe life into fault mechanics. If gentle electromagnetic nudges exist, this breathing is the ideal probe, more sensitive than major quakes, less noisy than aftershock swarms. Recent cycles are well enough documented to compare with distinct space weather phases. But again, pre-registration and blind controls are armor against overreach. In summary, history does not replace present data. It offers a catalogue of candidate windows and a list of cognitive traps. It shows that convergences happen, and most times yield nothing beyond expectations. It teaches us to use peak seasons with discipline, set criteria ahead, keep notebooks, and accept silence as valid results. Human archives also carry comet lore. Halley's 1910 apparition was a global media milestone, inflating fear of a cyanogen tail in the sky. Big quakes occurred around that time, but not beyond tectonic norms. It was perfect emotional fodder for a comet quake tale, yet poor on evidence. It's a modern lesson. Collective emotion amplifies perceived risk far more than actual odds. Positively, that teaches communicators how not to sensationalize 3i Atlas. Medieval chronicles, East and West, record tailed stars near earth-shaking or floods. But these lack quantified detail, no precise timing, brightness, or coordinates. Earthquake records come only from damage reports skewed towards survival bias. Big events remembered, quiet skies forgotten. Responsible mining here means multi-source cross-checking Chinese astronomy alongside European annals, an orbital back calculation of candidate comets. Complex work, but it may yield a few usable anchors. Modern clusters tempt imagination. Sumatra 2004, Chile, Japan 2010 to 2011, Halloween storms 2003. But laying them side by side, the first act is stripping away emotional overlay. Each quake had deep tectonic drivers. Each storm had its solar origins. Life paths may cross in time, but are not automatically joined in mechanism. A cleaner historical route is to digitize physical indicators, sunspot numbers, geomagnetic indices, PC5 oscillation frequencies, TEC variations. These can be standardized and compared across cycles. If someone claims solar maximum seasons slightly raise aftershock rates in giant quake regions, that is testable. Pick M greater than or equal to 8.5 aftermaths, slice by maxima/minima. Compare aftershock timing. Comets then become secondary triggers at most. And if even maxima show no consistent shifts, it is hard to argue that a comet alone could matter. On comets themselves, Hale-Bopp 1997 was a media lesson more than a space physics one. Its spectacular dust tail educated millions about radiation pressure and orbits, but no special EM windows emerged. By contrast, dimmer comets like Encke, whose ion tail was cut off by a CME in 2007, or others with leading brightness, gave scientists plasma puzzles. These quieter cases matter more for the 3i Atlas story. Structure of interaction, not visual drama, is the true signal. Another season is 1859, the Carrington Storm, the strongest pre-industrial geomagnetic blast. Auroras were bright enough to read newspapers, and telegraph systems sparked. Big quakes that year were unremarkable. Lesson: space weather can devastate technology without touching seismicity. A reminder relevant to 3i Atlas: if quake trigger hypotheses fail, storm-era infrastructure preparedness still pays off. Together, these slices guide a logic for comparative history. 1. Prioritize physical, digitizable markers, sunspots, indices, PC5, TEC, over law. 2. Focus on modern dense network eras. 3. When reaching back, use multi-source convergence and orbital back calculation. 4. Apply pre-registration and blind controls even to historical datasets. 5. Stress test any hints with competing natural mechanisms before calling them unusual. For US culture, this also sets a communication duty. Spark curiosity without sowing panic. American audiences love mystery documentaries for their wonder, but expect transparency. When citing 1960s or 2011, pair with simple charts, sample bias explanations, and methods. When retelling Halley 1910, include the cyanogen panic as a case study of media bias. When describing Carrington 1859, link to today's grid hardening protocols. This makes history practically useful. Above all, history reminds us of Earth's slow breathing. Faults load over decades and centuries. The sun breathes in 11-year cycles and beyond. Comets drop in on their own clocks. Overlaps are inevitable. Meaning only emerges from patterns stronger than chance. That is why every season of convergence should become a season of disciplined observation. Set criteria, record both silence and sound, and build bridges from story to science. When mining history, prioritize digitizable physical markers, sunspots, geomagnetic indices, TEC, PC5 oscillations, dense modern eras, and cross-source alignment. Avoid relying on lone omens. Carrington 1859 shows storms can hit infrastructure without quakes. Halley 1910 shows media bias can inflate fear. The right frame is to turn convergence seasons into test seasons with pre-registered criteria and controls. I enjoy combing through history, but the more I read, the more I value carefully recorded silences. Bright skies without shaking, quakes on ordinary nights. Both halves complete the picture. For 3i Atlas, if history speaks at all, it whispers this: shine the light of data into places without a story. That is often where truth resides. Part 7. The October 2025 critical window. As the astronomical calendar turns to October 2025, we enter a time frame where multiple important variables converge. Space weather experts call this the critical window, not because of a predicted catastrophe, but because of the convergence of factors that may amplify one another in unpredictable ways, if not observed with disciplined planning. 3 prominent elements define the backdrop. The sun's activity is in a high phase. High-speed streams from coronal holes tend to recur with the star's rotation, and 3i Atlas moves into a stage of strong activity before and around perihelion. Together, they form a natural laboratory with stimuli long enough for the geospace system to respond in resonant modes, yet varied enough for us to compare many cases in a single month. Let's reset the picture. The low-frequency oscillation band of geomagnetism, often called PC5, can be enhanced when the magnetotail is compressed and disturbed by stable, high-speed solar wind. These oscillations, lasting for hours, can phase lock with the magnetosphere's intrinsic resonances, creating a more persistent electromagnetic pulsation compared to the quick strikes of coronal mass ejections. Theoretically, if 3i Atlas, with its large coma and sensitive ion tail, produces slight phase shifts in the interplanetary field, or simply reflects the wind's structure in an organized way, then the PC5 band would be the first to show traces. We do not expect a sudden jump in amplitude, but rather subtle, persistent variations, like a heavier baseline added to a familiar score. The critical window also has an important astronomical component: geometric alignments. When the moon is in its new phase, the chain linking sun, moon, and Earth subtly changes gravitational fields and atmospheric tides. These effects are not large enough to trigger earthquakes, but they can modulate the amplitude of some ionospheric and magnetospheric resonances, like slightly turning the gain knob on an amplifier. If, at the same time, A high-speed stream flows in, and the PC5 band is primed, the system becomes more sensitive to long-lasting stimuli. Furthermore, the angles between solar wind direction, Earth's rotation axis, and the orientation of the interplanetary magnetic field determine the effective window for dayside reconnection, shaping the upstream, midstream, downstream chain of events. The critical quality of October also comes from the human rhythm. This is when North America enters late autumn. Energy demands shift. The power grid runs in a different configuration, and polar airline routes adjust seasonal schedules. Our technical systems become more sensitive to prolonged disturbances. If we treat 3i Atlas as a natural sensor embedded in the solar wind, then late 2025 is when this sensor passes through a testing ground thick with targets and filled with ground-based instruments to synchronize data. For a scientific documentary, this is gold. The audience gets to follow a campaign season with clear milestones, rather than vague claims. So how should we prepare for this window? First, the research community should publicly release baseline criteria. What PC5 increase counts as significant compared to seasonal median? At what latitude GNSS, total electron content variability, becomes structurally anomalous? And what threshold of ground electric field variations exceeds instrument error? Laying these numbers out in advance protects us from calling every fluctuation a signal. Second, target regions such as southern Alaska, Cascadia, and locked segments of the San Andreas should raise their monitoring vigilance, not to issue seismic warnings, but to ensure continuous data. Seismometers working, GNSS gaps avoided, magnetometers transmitting steadily. Third, groups observing 3i Atlas should standardize their methods for measuring coma and tail morphology, using the same algorithm for extracting tail orientation, curvature, and rotation-linked variability. A useful tactic is to establish data shifts across time zones so that whenever a clear phase shift appears at L1, within 1 or 2 hours, the magnetosphere ionosphere group has updated PC5 and TEC plots, while the infrastructure group receives ground electric field reports. When all 3 channels light up together, target seismic regions can annotate logs, marking microseismic clusters or altered slow-slip rhythms if present. For viewers, knowing there is a round-the-clock scientific team brings reassurance. This is not a dreamlike signal chase, but a well-organized effort. We must also prepare mentally for a dull outcome. The critical window passes, and everything behaves like a normal solar maximum season. That is not useless. It provides a control for future critical windows and sets upper bounds for effect amplitudes, if any. Conversely, if a few sub-windows in October repeatedly display pre-registered patterns, the following weeks will focus on distinguishing 3 possibilities: pure natural magnetospheric resonance, structured reflection linked to 3i Atlas but without downstream effects, or subtle downstream impacts visible in microseismic activity. Each path leads to a different analysis sequence, and having criteria preset saves time in debate. A special reminder for the media: tell the story by the rhythm of data, not the rhythm of emotion. Instead of headlines about a gateway to disaster, explain why long-lasting oscillations are worth monitoring, why infrastructure requires extra attention during such phases, and why even without seismic links, this research still pays dividends. American audiences value transparency, and they will stay engaged if they feel treated as partners, not as clickbait targets. Finally, the critical window is a good chance to practice what is always scarce: open data. If groups share near real-time composite indices, release open-source PC5, tech, and electric field codes, and quickly publish null windows, trust will thicken. Even if the scientific results are not spectacular, the remaining legacy will be a new standard of collaboration for future interstellar rendezvous seasons. The October 2025 critical window is defined by high solar activity, recurring high-speed streams, favorable astronomical geometry, and strong activity from 3i Atlas. The PC5 band reflects long-resonance magnetospheric oscillations, while GNSS tech and ground electric fields serve as midstream and downstream indicators. Scientific preparation includes pre-registering thresholds, securing monitoring infrastructure, synchronizing comet upstream magnetosphere teams, and setting up data shifts by time zone. I prefer to call this October a season of discipline rather than mystery, because if anything worth noting occurs, it will emerge naturally on the pre-arranged charts. And if not, we still leave the season with a tighter network, cleaner procedures, and one small but valuable lesson. When many variables surge together, that is when we must remain calmest. For the critical window to become a true grand exercise, we need an operational script that carries us from data to provisional conclusions in each case. Imagine a typical mid-October day. Before dawn on the East Coast, the upstream dashboard shows rising wind speed at L1, density dropping below the seasonal baseline, and BZs stably southward for hours. At the same time, the 3I Atlas team reports coma brightness variations linked to inferred rotation and an ion tail slightly off the textbook anti-solar direction, hinting at more complex field interactions. The US time zone shift switches the window open flag to yellow, alerting downstream groups. In the magnetosphere ionosphere tier, PC5 plots at mid-latitudes begin to thicken. This is not a bursting geomagnetic storm, so summary indices like KP do not spike. But that is exactly what makes the case interesting. It is the long resonance we are waiting for. GNSS, total electron content maps, show structured variability drifting toward the night side, consistent with a lightly but steadily compressed magnetotail. Meanwhile, ground electric field stations in the northeast register slow, steady amplitudes exceeding the seasonal median by 1 to 2 standard deviations for hours. These signals are enough to turn the flag from yellow to orange. We enter the look closely phase. In this phase, filtering local noise is critical. Stations near power lines, railways, or industrial areas can mimic ground electric field signals and must use event filters aligned with operational schedules. In GNSS data, mild solar storms can blend with seasonal tropospheric noise, so algorithms must remove daily trends before declaring anomalies. In magnetometer data, local thunderstorms can contaminate readings and must be excluded from the sample. Only when these filters strip away background chatter do the remaining plots deserve to be called candidate signals. From there, the question shifts to seismology. In southern Alaska, seismic arrays record a slight uptick in mid-depth microseisms scattered along a fault segment that has already hosted weeks of aftershocks. In Cascadia, slow slip monitors see nothing beyond the region's own background rhythm. In California, GPS slip rates on a few partially locked San Andreas segments oscillate around the average, showing no meaningful deviation. Such mixed signals are normal in natural experiments. Not every place sings the same tune, and regional differences are precisely what we need to learn from. The scenario will repeat many times during the month. Some windows open without notable seismic activity, others coincide with slight microseismic increases. At the end of each week, the synthesis team publishes a public technical bulletin: hours of PC5 above threshold, hours of structured tech anomalies, hours of ground electric fields exceeding limits, and all seismic or geotechnical changes surpassing reporting standards. Each bulletin comes with 2 control tables, one from false windows, in September when space weather was calm, and one from less sensitive regions, e.g., southern continental interior, during the same window. If one week seems noisy, the controls tell us what percentage of that noise is truly unusual. A helpful supplementary analysis dimension is time-frequency space. When we suspect a long-period stimulus is striking the system, staring at raw time series can be misleading. Dense data hides small oscillations in noise, but switch to the frequency domain and a thickened PC5 band stands out as a ridge. Similarly, if ground electric fields tend to strain on tens of minute cycles, station spectra maps will show regional features clearly. In microseisms, distributions of inter-event intervals may reveal slight clustering when the background is nudged. No single chart alone can convince, but a small ensemble pointing in the same direction elevates point to line. In all cases, what must be avoided is slipping into retrospective storytelling, seeing an event first, then narrating how it fits expectations. The antidote is to log each window with a preset examination sheet. Upstream conditions, magnetosphere ionosphere status, downstream seismic structural notes, all numbers filled into boxes. The sheet allows for nothing observed, and ticking that box is a valid scientific act. By the end of the month, we hold a large matrix of filled cells, and any patterns, if real, emerge statistically, not from imagination. The critical window is also a chance to stress test infrastructure communication chains. When ground electric fields exceed thresholds for hours in the north, do grid operators acknowledge, log minor induced current anomalies, and adjust local loads? When tech varies strongly, do positioning services apply advanced ionospheric filters? When PC5 extends, do airlines activate backup polar routes? Whether or not the seismic hypothesis succeeds, these communication channels, if smooth, are tangible byproducts of the whole campaign. And of course, we must allow room for surprises. A mid-sized CME might barge in, masking the long resonance we aim to study. 3I Atlas might enter an unusual activity phase, making its ion tail sway in unprecedented ways. In such cases, we record and flag them as interference cases, keeping the criteria intact. Discipline does not kill curiosity. It protects curiosity from being carried away by coincidence. By the end of the month, suppose no large earthquake wakes up the public. This is the most common and welcome outcome. The final summary would then emphasize on 3 points: whether electromagnetic signal chains showed repeating patterns linked with 3I Atlas morphology and inferred cycles, whether target regions displayed statistically shifted microseismic or slow-slip behaviors, and what operational lessons from data quality to coordination protocols need refinement. Then, October's story becomes a model case study in how to do science during a season full of mysteries without chasing sensationalism. Operating a critical window requires concrete procedures: detect upstream phase shifts, confirm long resonance baselines in PC5, TEC, and ground electric fields, filter local noise, compare with insensitive regions and false windows, analyze in time-frequency space, and log by pre-registered sheets. All conclusions must stand on multi-layered data matrices, normalize thresholds, and respect for physical delays. Cooperation with infrastructure, power, aviation, navigation is a parallel track delivering benefits independent of seismic hypotheses. I picture October as a long concert where we hold the score in hand. We know the conductor may be the sun. We know there is a strange guest named 3I Atlas. And we know Earth's orchestra sometimes plays upbeat, sometimes solemn. Our role is not to shout at every high note, but to listen for themes that return at least 3 times to become motifs. If they do, we write them into the full score. If not, we still leave the hall with sharper ears. Part 8. The Comet Swarm and Amplified Energies. If 3I Atlas is the main character of this season, then its retinue is a whole swarm of expeditionary guests, the comets visiting the inner solar system at the same time. To the audience's eyes, this is a visual feast. To the eyes of space physics, this is a valuable mosaic. Multiple plasma interaction sources operating in parallel, each plugged into the flow of the solar wind at its own angle, orbital altitude, and internal rhythm. It is precisely this diversity that creates the chance to measure the synthetic amplification of small variations that, taken individually, might not be large enough to detect. The concept of synthetic amplification here is not a raw addition of energy. Each comet, with its coma and ion tail, slightly distorts the local field and plasma structures it passes through. Hundreds of millions of kilometers away, We do not expect those distortions to directly bridge into the magnetosphere. But when multiple sources of interaction are active in the same time frame, the probability rises that the solar wind contains repeating, extended ripples, a kind of smoother background music. And as discussed, the magnetosphere responds more sensitively to persistent background music than to short bursts of thunder. The comet swarm, in that sense, does not need to be strong, only steady and multi-point. The specific mechanism can be imagined as follows. Each comet has a transition region where neutral particles are ionized and swept into the field, creating a cloud of ions with little initial energy. As the solar wind sweeps past, these clouds act like tiny electromagnetic friction zones, places where wave and particle energy can exchange through local resonances. From afar, the wind passes through a series of plasma anchors and accumulates small phase shifts in the wave spectrum. A single anchor creates only a blur. A line of anchors can create a flowing skirt in the spectrum, extending for days. That is the kind of rhythm the magnetosphere likes to lock onto. Of course, this scenario only matters if it produces testable predictions. First, upstream at L1, we would expect to see a wave spectrum with a PC5 background thicker than normal during intervals when multiple comets, not just 3, I-Atlas are strongly active. This does not require high amplitude, only persistence and slightly more structure than the seasonal background. Second, in comet radio and optical data, we would expect to see a slight degree of synchronization between morphological indicators, such as ion tails bending at slightly unusual angles across several objects within the same window. Not all, just more than chance. Third, if the PC5 background really does thicken for long periods, the ionosphere will breathe along. GNSS total electron content maps will show latitude stratified, time local oscillations, measurable across North America when geometry is favorable. The appeal of the comet swarm also lies in the spatial controls it allows. Suppose in the second week of the month, PC5 background thickens and tech oscillates smoothly, but in the third week, both thin and fragment. If comet activity calendars show more simultaneous peaks in the second week and fewer in the third, that is nearly a natural experiment. Conversely, if PC5 thickens in both weeks, while comet activity differs greatly, the swarm's amplification role must be reconsidered. The strength of this strategy lies in comparisons between mini-seasons within the same month, where the sun does not change much, but the visiting team takes turns on stage. An under-discussed but important aspect is the memory of the system. The magnetosphere and ionosphere are not instantaneous systems. They have transient responses. A thick PC5 background today may leave aftertones in field-aligned flows and ionospheric charge distributions the next day, especially if wind field configuration remains steady. The comet swarm, therefore, does not need to all play at the same hour, only to form a sequence tight enough that the system never fully returns to rest. Under such conditions, multi-hour ground electric field variations become more common, and it is precisely those persistent stimuli that any gentle triggering mechanism, if it exists, would be sensitive to. For the downstream seismic structural layer, the comet swarm does not change the logic. Faults only respond when near threshold. The difference lies in the resonance factor. A smooth, long-duration stimulus can penetrate deeper into natural conductivity networks and create micropore pressures in more phase-coherent ways than abrupt jolts. If a region is sensitive, it will be more sensitive on such days. On the ground, the signals to seek remain. Micro-seismic warming clusters at intermediate depth, small shifts in slow-slip rhythm, or fluctuations in GPS slip rates on partially locked segments. And as always, blind controls and pre-registered thresholds protect us from seeing patterns everywhere. At the infrastructure level, the comet swarm simplifies communication. Instead of speaking about a single strange visitor, we talk about a plasma season with multiple interaction sources. This storytelling is closer to how people understand storm seasons. No one asks which individual storm caused the rain, but whether the season was wet. For power and navigation sectors, what matters is the prolonged background of disturbances affecting transformer thermal fatigue and accumulated ionospheric errors more than sudden spikes. In a plasma season, proactive maintenance schedules, load distribution, and adaptive filters deliver immediate benefits without waiting to resolve 3I Atlas's seismic role. Naturally, there is also the silent scenario. The comet swarm leaves no imprint. Upstream, midstream, downstream all behave like an ordinary solar maximum season with no extra structure. This scenario is equally valuable, for it establishes a baseline for future encounters. What level of PC5 oscillations is normal in a comet-rich month, how tech typically varies with latitude, and how much the ground electric field usually fluctuates. Such a baseline becomes the yardstick against which all future anomaly claims must be measured. A final point worth emphasizing: the swarm helps us avoid a strong psychological bias causal attribution. Humans tend to seek a single, specific cause for every phenomenon. But the interplanetary plasma environment is an orchestra, not a solo instrument. When we step back and listen to the whole, we stop being fixated on one violin and start hearing the background, the true determinant of which rhythm the magnetosphere will dance to. From that angle, the question, did 3I Atlas cause quakes, transforms into, does a plasma season with amplified background raise the conditional probability of gentle triggering where faults are near threshold? A humbler but more scientific question. The comet swarm may create synthetic amplification by making the solar wind wave spectrum more persistent and structured without needing high amplitude. 3 test indicators. PC5 background thicker than normal during multi-comet activity windows. Slight synchronization in ion tail morphology across several objects, and latitude stratified tech breathing in the same time frame. The magnetosphere has memory, so sequence matters as much as simultaneity. Downstream, the signals remain microquakes, slow slip, and slip rate fluctuations, all requiring blind controls and preset thresholds. I always find it easier to breathe when shifting from single culprit to background season. The universe rarely performs monologues. It is a chorus. If Earth ever responds with a strange note, I lean toward the idea that the orchestra has changed its tune, rather than one instrument suddenly casting a spell. And precisely because of that, I value patient measurements that build bridges from background to peak, from spectrum to single note. From the comet swarm, we turn to a practical question. How do we turn this multi-source context into a clean, informative measurement without falling into the trap of everything explains everything? The answer lies in designing a synchrony matrix with 4 axes: astronomical calendar, upstream wave spectrum, magnetosphere ionosphere response, and downstream technical seismic indicators. Each axis has simple, measurable quantities published in advance, so the community can cross-check week by week. The astronomical calendar axis records each comet's state, date of peak brightness, activity indicators such as coma brightening rate, light/dark asymmetry, leading brightness, ion tail angle relative to the sun, and day-to-day variability. These are then consolidated into a daily swarm index, say a 0 to 10 score, reflecting how many comets are strongly active and how morphologically diverse. The upstream wave spectrum axis comes from ELS-1 satellites, PC5 and PC4 wave energy, persistence hours above threshold, and repeating spectral features such as shoulders or ridges. The magnetosphere-ionosphere axis uses PC5. Amplitude by latitude band, a tech rhythm index describing time local regularity, and ground electric field deviations from seasonal median. Finally, the downstream axis has 2 branches: technical, ground-induced currents, grid operator logs, positioning errors, and seismic structural, microseismic rates, slow slip, GPS slip rate fluctuations. When this matrix runs, what matters is not every cell lighting up at once, but diagonals. Days when the swarm index is high, upstream PC5 background thickens, Ground PC5 lines bolden. TEC shows rhythm, and microseismic upticks appear in already active regions. If a few such diagonals emerge within a month, we may speak of a pattern, not yet a mechanism. Conversely, if the swarm index fluctuates but other axes stay silent, or PC5 thickens on days when the swarm is sparse, the swarm's amplification role must be downgraded. A subtle but useful element is apparent locking among comets. Within a span of days, if 2 or 3 objects show similar ion tail asymmetry, say bending 10 to 15 degrees off the antisolar line, and that asymmetry disappears when wind phase shifts, then we have a morphological indicator acting almost like a clock to compare with spectra. The morphological synchrony need not be strong, only above a random baseline. If on the same day, upstream wave spectra also show a small shoulder in the corresponding frequency band, the diagonal between axes grows convincing. Place 2 such diagonals together and project onto the magnetosphere-ionosphere axis, and ground PC5 lines are more likely to bolden on the same day. In this way, the swarm can be quantified beyond perception. From a practical perspective, the swarm season is also a chance to test machine learning tools cautiously, not to predict quakes, but to detect prolonged background patterns in multi-layered spectra. A simple feature set, average PC5 energy, persistence, tech rhythm index, hours of ground electric fields above threshold can feed a 2-class classifier, high swarm day versus low swarm day based on pre-registered astronomical index. If classification accuracy significantly exceeds a random baseline under blind cross-validation, we know the swarm leaves measurable signatures in near-Earth plasma electromagnetic layers, independent of seismology. This result alone is valuable. It says the near-Earth solar system hears the background from many small interaction sources. Meanwhile, the downstream technical branch allows testing a practical hypothesis. Does a prolonged plasma season increase system fatigue? Power grids are sensitive to cumulative ground-induced currents. Navigation accuracy is sensitive to sustained ionospheric turbulence. Instead of waiting for outages, we measure small symptoms. The number of transformer temperature alarms unrelated to load. The hours GNSS had to activate advanced ionospheric filters. Count of stray current reports on transmission lines. If such symptoms increase in weeks, when the swarm index and PC5 are both high, that is another diagonal not seismic, but practical for infrastructure operations. The good news, this conclusion is useful even if the gentle triggering hypothesis is refuted. At the seismic level, the golden rule remains. Where near threshold, they're sensitive. Analyses should focus on regions fresh off major events, dense aftershocks, or regions with a history of steady, slow slip. In the swarm season, we check whether microseismic warm-ups precede extended PC5 TEC phases. Even if they do, the proper reporting is as conditional probability increase with small values, not categorical warnings. For example, during days with continuous PC5 background for 8 hours and rhythmic tech, the chance of a slight microseismic cluster in the next 48 hours in region X rises from 5% to 7%. This phrasing stays true to gentle triggering, not creating, only modulating timing and amplitude of what already exists. One ever-present danger is retrospective piling. The comet swarm is rich in story material. The mind easily stitches observed fragments into persuasive narratives. The antidote is whiteboards. Before each week, the analysis team writes down 3 questions to answer at week's end, with evaluation criteria. At week's end, we answer exactly those 3, no more, no less. If the result is negative, it goes into the archive as a baseline brick. If positive, it goes in as a candidate. After a month, the archive is large enough for statistics to speak instead of intuition. We must also mention storytelling with the public during this season. American audiences are used to weather reports. The plasma season can borrow that style. overview maps, a few simple indices, short notes on infrastructure impacts, and a clear emphasis that seismic implications, if any, remain only at the background condition level. Avoid language like comet horde attacks or cosmic seismic storm, which, while attention-grabbing, erode trust. A reasonable framing would be, this week, several comets are strongly active. We expect ionospheric disturbances to be more prolonged than usual. Power and navigation services have increased monitoring. In active fault regions, microseismic tracking is closer, but no special alerts are issued. An ideal outcome of the swarm season would be a new set of standards for integrated observation campaigns. Next time, even without 3i Atlas, we will still have a swarm index, a PC5 rhythm index, a tech rhythm index, and infrastructure comparison protocols. These tools turn a season of mystery into a season that upgrades community capacity. And if a few diagonals stand out clearly this season, they become seeds for sober scientific papers with modest titles, promising no more than the data allows. To measure the comet swarm's synthetic amplification, build a 4-axis matrix, astronomical calendar condensed into a swarm index, upstream wave spectrum, PC4 to PC5 energy and persistence, magnetosphere ionosphere response, PC5 thickness by latitude, TEC rhythm index, ground electric fields, and downstream indicators, power grid GNSS technical data, seismic structural data. Look for synchronized diagonals, not for every cell to light up. Use blind tests, pre-registered weekly questions, and end-of-period statistics to avoid retrospective bias. I prefer the feeling of casting a net over throwing a spear. The comet swarm makes the sky fascinating, but what reassures me is the preset matrix of criteria. When the net is stretched at the right tension, whether big or small fish happen to swim through, we still see ripples. And if the net comes up empty, I take it as another kind of fortune. Knowing the sea this season is calmer than we imagined, and that we have learned how to fish without disturbing the waters. Part 9. Solar maximum meets interstellar comet. There are moments in the history of the solar system when great rhythms overlap, creating a rare chord. The solar maximum is one such rhythm. The number of sunspots increases. Magnetic field structures from the surface to the heliosphere twist more complexly. The sun's differential rotation stirs magnetic tubes, and energy release events occur more densely. Into that background, place an interstellar visitor, like 3i Atlas, and we gain a natural lever to ask big questions about plasma interactions and the role of natural probes in exposing the heliosphere's vast currents. First, the solar maximum is not just more eruptions. It is a geometric reconfiguration of the entire Parker spiral, the giant current sheet wrapped around the solar system by the solar wind. At minimum, this sheet is flatter, near the solar equator with a fairly clear split. Fast wind from polar coronal holes, slow wind from the equatorial belt. At maximum, the boundary blurs. Coronal holes can appear at low latitudes. The current sheet ripples with large amplitudes, and the boundaries between wind regimes become patchy. This is the ideal context for wave-particle processes, reconnection, and resonances to be naturally amplified. An interstellar comet with a large coma and sensitive ion tail acts like a planet-sized passive antenna. When the solar wind floods across the coma, neutral particles are ionized by high-energy photons and charge exchange, becoming pickup ions. These newborn ions are initially nearly stationary in the solar wind frame, so they are dragged by the field, start cyclotron motion, and gradually merge into the flow. This process is not silent. It generates alpha-n waves, excites microturbulence, and can subtly alter the spectrum of the flow. If 3i Atlas is large enough in plasma cross-section, the interaction region is not just a glowing green tail, but also a small wave furnace within the Parker spiral. At solar maximum, when magnetic field lines twist and burst, adding such wave furnaces into the flow makes energy transfer geometry more interesting. Alpha-Veen waves can travel along curved lines, reflect at strong gradients, and form local standing patterns. Observationally, this means upstream spectra may thicken persistently without the need for CME strikes. And as discussed, Earth's magnetosphere responds most strongly to persistent wave backgrounds. On the other hand, maximum also increases the probability of dayside reconnection when the interplanetary magnetic field stays southward. A slightly fast wind, slightly low density, and continuous southward BZ for hours or even a day form the magnetosphere's favorite meal if it wants authentic resonance at low frequencies. If on such days, 3I Atlas is in its active phase, with rotation cycles making the ion tail beat rhythmically, then the window for testing the structured reflection hypothesis opens wide. The story grows more compelling when we recall that maximum raises the number of low-latitude coronal holes. These holes fire fast streams with approximately 27-day solar rotation recurrence, forming co-rotating interaction regions when fast wind catches slow wind. These extend for days and form organized wave planes. For 3I Atlas to pass through such regions is like sweeping across a rippling field. In such conditions, the comet's subtle rhythm is more likely to inscribe itself onto an already structured wave background. Not because the comet grows stronger, but because the stage is ready for a fine brushstroke. For our cameras, the maximum is also the season of blossoming sensors. From upstream at L1 to near-Sun satellites to low-Earth orbit spacecraft and ground networks, all are collecting dense, multi-channel data. This is a major difference from the famous comets of the past century. In the Hale-Bopp era, we mostly observed with eyes and telescopes. Now we observe with spectra. This enables a kind of cross-matching never before possible, aligning comet morphology rhythms with upstream spectral rhythms, then with ground PC5, and finally with ionospheric breathing. Downstream, the sensitive question returns. Can maximum's long background be enough to nudge faults near threshold? The cautious answer remains, possibly in timing adjustment, not causation. If gentle triggering exists, maximum provides the optimal background to detect it, because the system is being scratched more evenly, more persistently. But for this very reason, test design must be stricter, respecting delays, using blind controls, and setting thresholds in advance. Maximum increases the chance of false patterns, because so much is simultaneously dynamic. Only discipline prevents being seduced by spectacular coincidences. A useful metaphor here is a fluid lab. At low flow speeds, a small object dropped in makes only ripples. When flow speed crosses a threshold, small ripples can link up, forming standing waves in the channel. 3I Atlas is a small object. The maximum is the highest flow. The right question is not whether the small object strikes the flow, but whether the flow is in a regime where small ripples can form standing waves. For the public, maximum is an emotional catalyst. Auroras descend to lower latitudes, solar images flare brightly, and news of GPS disruptions or polar flight adjustments sparks curiosity. This is the moment to frame 3I Atlas correctly, as a natural antenna helping us see the invisible, not as a culprit. That framing is both truthful and engaging. It makes viewers feel like they are witnessing an open experiment of nature, with all variables labeled. Finally, maximum reminds us of long rhythms. When the 11-year cycle peaks, we tend to exaggerate the present. But in the next cycle, there may be no interstellar comet alongside. Thus, every effort today should aim for legacy. Procedures, criteria, open data, and comparison tools. One well-documented rare chord becomes a textbook for generations, regardless of whether gentle triggering proves real or not. The solar maximum is not just more eruptions, it is the restructured Parker current sheet, low-latitude coronal holes, large wave current sheet, wind organized into co-rotating interaction regions. 3I Atlas is like a passive plasma antenna producing pickup ions, exciting alpha-Venn waves and potentially thickening persistent wave spectra. 3 observational layers should be cross-matched: comet morphology and rotation rhythms, upstream spectra, and ground PC 5 plus TEC responses. all under the discipline of delay and blind controls. I see maximum as a fully lit stage. When the lights blaze, even small objects cast long shadows. 3i Atlas may be only a small object on that stage, but its shadow helps us see the grain of the floor. If we leave this season with better maps of those grains, I will call that a beautiful ending to a properly told story. If the previous section set the physical context of maximum, this section dives into how a handshake between an interstellar comet and the solar system might leave measurable signatures. Bold hypotheses are not needed, just known pieces. Pick up ions in the coma. Alpha-Ven waves along field lines, co-rotating interaction regions nurturing persistent waves, and the magnetosphere strongly reacting to low-frequency rhythms. From this, we build a test chain. From 3i Atlas's rotation rhythm to upstream spectra, to ground PC5 bands, then into familiar ionospheric markers. The first piece is 3i Atlas's rotation rhythm. Many comets show rotation periods of hours to tens of hours. If the coma and ion tail of 3i Atlas display repeating asymmetry by rotation, we have a natural rhythm source. In a solar wind regime structured by a maximum, this source may faintly mark upstream spectra, like a bass note repeating in a dense composition. Finding that bass note is not easy, but there is a roadmap. Align comet morphology observations with satellite spectra, then check if a stable energy ripple appears in a frequency band consistent with the inferred rotation period. No large amplitude needed, just more recurrence than chance. The second piece is the transmission path from upstream into the magnetosphere. When BZ stays southward for long, the dayside reconnection window opens. Low-frequency ripples can penetrate deeper, exciting magnetosphere resonances. Here, delay is key, minutes to hours, from L1 to the magnetopause, plus tens of minutes for PC5 to thicken. If a low-frequency trace is truly present upstream and meets steady southward BZ, we expect ground PC5 bands to bolden more than on a day with strong wind, but fluctuating BZ. This leads to the third piece, ionospheric response. GNSSTEC usually breathes daily, but on a persistent PC5 background, that breathing becomes more structured, forming latitude bands visible on dynamic maps. The fourth piece is the filter of infrastructure. Not all electromagnetic variations matter to grids or navigation. Grids are sensitive to ground-induced currents lasting minutes to hours. GNSS is sensitive to sustained ionospheric turbulence and tech fluctuations. Thus, if PC5 persists with southward Bs and 3i Atlas's rhythm faintly appears upstream, these systems may record more hours of fatigue than normal. Whether or not seismic hypotheses hold, operations benefit directly from tracking these long rhythms. To avoid over-interpretation, we need independent anchors. Anchor 1. A non-interstellar comet. If a smaller, less active solar system comet passes simultaneously, does it produce similar signatures? If yes, interstellar importance drops. If not, 3i Atlas deserves closer attention. Anchor 2. Maximum weeks without notable comets. If PC5 thickens with a similar structure, then comet linkage must be down-weighted. Anchor 3. Magnetohydrodynamic models. These allow feeding observed upstream conditions into simulations and predicting PC5 responses. If models reproduce most PC5 features without a comet rhythm source, then only the residual deserves candidate status. Another verification branch lies in the lab. Plasma experiments in tubes or magnetic traps can reproduce a miniature version of pickup ion and Alpha-Ven wave processes. Insert a neutral source into a magnetized plasma flow, toggle it periodically, and measure whether wave spectra show ripples in the compatible band. Scaling cannot match space, but the principle can be checked. Such experiments separate nice-sounding idea from mechanism with teeth. In forecasting terms, maximum allows a modest but useful type. Background condition outlooks. Instead of storm forecasts, we issue persistent background outlooks. A bulletin might say, in the next 48 hours, Based on upstream data and activity of 3I Atlas and the comet swarm, the PC5 background is likely to stay above the seasonal median for hours at mid-latitudes. Recommendations: grids increase, GIC monitoring, GNSS services activate advanced ionospheric filters, seismic groups in active regions ensure stations run without gaps and track clusters. Such bulletins are useful even if nothing special follows, because they build habits of synchronization between monitoring and operations. A legitimate concern is phantom signals. Maximum brings many simultaneous factors: CME, fast wind, BZ variations, and seasonal ionospheric noise. How do we ensure faint spectral ripples are not just natural products of those? The answer: multi-cycle statistics. If the same detection procedure finds base notes in past maxima without the 3I Atlas, with a low false alarm rate, confidence grows. If the procedure only finds rhythm when Atlas is known in advance, that signals bias. Similarly, blind testing across groups, one group seeing only upstream spectra, another only comet morphology, reduces seeing what we want to see. And the hot question: if all layers nod, should we issue seismic alerts? The honest answer for American audiences is no. Seismicity is a conditional probability story, and any effect would only shift timing near thresholds. What should be done is remind communities to follow existing preparedness, emergency kits, family plans, and evacuation routes. At the same time, make clear that this campaign aims to study plasma background and infrastructure impacts, with seismic as a side branch needing years of data before reliable claims. Finally, the Maximum and 3I Atlas are a test of our scientific integrity. If we can tell a compelling story without exaggeration, set criteria in advance, publish nulls, keep data open, and invite critique, then regardless of the conclusion, we will have taken the right path. With a subject so easily tempting to imagination, that is the most important victory. The verification chain at Maximum includes 3I Atlas's rotation and morphology asymmetries as rhythm source, upstream spectra seeking repeated ripples under physical delays, ground PC5 thickening under prolonged southward buzz, and ionospheric responses measured by tech. Anchors include inner system comets, maximum weeks without comets, and MHD modeling of the magnetosphere. Plasma labs can confirm pickup ion and wave excitation principles. The useful forecast is persistent background outlook for infrastructure, not seismic alerts. I feel most reassured when a grand story withstands small questions. Where is the rhythm? How long is the delay? Is the ripple strong or just persistent? Does the model reproduce most features without the main character? When small questions are properly answered, the story, whatever its end, nurtures trust. And trust, in both science and society, is always the most precious foundation. Part 10. Directed energy, or natural phenomenon. At this point, we have assembled nearly enough physical pieces to trace the long rhythms in near-Earth space. But one difficult question still stands at the threshold, awaiting a more decisive answer. Could everything we observe be purely natural, or is there any door open to a bolder interpretation? Something like intentional influence, akin to directed energy. Before approaching that provocative hypothesis, it is crucial to build the right guardrails. The first guardrail is Occam's razor. If a set of natural mechanisms already suffices to explain the thickest layer of data, then there is no valid reason yet to invoke an intelligent agent. The second guardrail is energy and dynamics. Any hypothesis about directionality must respect the limits of energy transmission in the solar system's plasma and magnetic environment, along with the reality that even extreme events like record geomagnetic storms rarely leave distinctive seismic marks. Why then does the directed hypothesis remain attractive? Partly because human intuition easily seeks intent behind spectacular coincidences. Partly because 3I's Atlas comes from outside the system, sparking imaginations of alien technologies that could harvest energy, by deploying massive plasma structures, and partly because our cultural archives are filled with stories of heavenly omens accompanying earthly upheavals. When we weave these threads together, the brain proposes a neat conclusion. If intent exists, the long rhythms we see might be test patterns checking Earth's response, but intuition must be stress-tested. The first question must be about signatures. How would a directed influence differ from natural background in a way today's sensors can detect? Think like a systems engineer. If someone wanted to knock on Earth's door with electromagnetic tools, they would need to multiplex against the enormous background noise of the sun. The best strategy would be to choose the frequency range and rhythm to which Earth's system is most sensitive. Here, the PC5 band and the magnetosphere's low resonances are candidates. An intentional influence, to be effective, would not try to boost amplitude crudely, but would exploit open states like prolonged southward BZ and choosing times when the system is listening. It would also aim for regularity, since Earth responds better to persistent rhythms than to quick strikes. This matches exactly what we already expect from natural mechanisms when stable high-speed wind arrives. In other words, the optimal strategy of an intentional action looks almost identical to the most effective natural pattern. This is the methodological paradox. When expected signs overlap with natural pathways, distinguishing the two by observation becomes doubly difficult. Still, there are ways to attempt separation. First path, spatial specificity. If a directed signal exists, it would not only boost the background, but also point. It could create longitudinal or local time asymmetries hard to attribute to natural drift. In ground data, this would appear as unusually bold PC5 regions compared to adjacent latitudes, persisting beyond day-night geometry variations. In tech data, we would look for distortions not following expected geomagnetic storm tracks. If such asymmetries repeat in timeframes not aligned with Earth's or the Sun's rotation, they are candidate signatures. Second path, temporal specificity. Natural background has strong rhythms. Day-night, the Sun's 27-day cycle, and wave transmission delays from Elwha's Sun to the magnetopause. A directed source would lean towards strange rhythms that don't match these three yardsticks. Practically, this means running spectral analyses against multiple reference frames. If a thin energy ripple reappears in the same frequency band when 3i Atlas is in active phases, but does not follow 27-day solar cycles, does not align with local time, and appears within the correct delays during southward BZ, then we have a noteworthy signature. The challenge is that the signature must repeat often enough to pass blind tests across seasons with and without 3i Atlas. Third path, cross-layer correlations with anomalous delays. A natural stimulus travels downstream with fairly fixed lags. A directed one, if not following the same path, may leave odd delay patterns. For example, ground electric field reactions preceding P. C5 detections by unusual margins or TEC variations out of phase with auroral maps. Thus, plotting cross-correlations across sensor layers is not just about watching rhythms, but about checking whether those rhythms travel the natural route. All these efforts remain under the shadow of the energy question. Even if an alien source had refined engineering, the transmission medium is tenuous plasma bound by conservation laws. ALF-VEN, wave amplification, cyclotron resonance, or reconnection all have efficiency ceilings in reality. More importantly, to tap faults, what matters is not absolute energy, but the ability to phase lock with Earth's natural conductivity pathways. That requires detailed knowledge of regional geoelectrical architecture, almost like an organ map of the planet at kilometer resolution. If a civilization had such a capability, it would also have countless quieter methods to probe. This is a modest but weighty argument in favor of the natural hypothesis. A practical framing for American audiences might be this. In risk insurance, people distinguish cyclical background risks from rare, fat-tail risks. Management differs, but both require dense data and causal structure respecting models. The directed hypothesis belongs to the fat-tail imagination category, compelling as a story, but the hardest to justify with evidence. Therefore, instead of rushing into the grey zone, we should focus on measuring and reducing noise in background rhythms, because whether or not there is a foreign hand, the background itself drives most impacts on infrastructure and public perception. In the end, we return to 3i Atlas with calmer eyes. If it is a giant plasma antenna, the best it offers us is the chance to peer deeply into the interface between solar wind and Earth's system. If it is only a dusty traveller with an unusual coma, we still gain a season of learning that raises our baseline standards and sharpens our discipline of interpretation. Both outcomes move us forward, as long as we keep our promise, never place conclusions ahead of data. Distinguishing natural from directed requires 3 test lines. Spatial signatures with asymmetries hard to reduce to day-night geometry. Temporal signatures with rhythms not tied to 24-hour or 27-day cycles but following physical delay windows. And cross-layer correlations showing delay patterns consistent with natural transmission. All analyses must be accompanied by blind tests across multiple seasons. MHD models reproducing responses without foreign sources, and strict energy constraints of plasma. Occam's razor and dynamical limits are the methodological guardrails. I like bold hypotheses because they force us to do our homework more carefully. But I have also learned that science's beauty lies in the courage to say, "not yet seen," even when that answer is less captivating. If 3i Atlas only teaches us how to listen to the background more carefully, that is already a great gift. The rest, if any, will arrive when we are ready to see it without stage lights dazzling our eyes. If we just set up methodological guardrails, now comes the roll-up sleeves toolkit. How to test, step by step, a bold directed hypothesis without falling into the too familiar traps of credulity or empty skepticism. My proposed approach has 4 nested layers: a Bayesian frame for managing belief, signal detection theory for quantifying hits and misses, pre-registration to restrain hindsight, and multi-source triangulation to ensure no signature stands alone. Start with Bayes. In every directed story, prior probability must be low because the explanatory cost is high. That does not mean closed. It only means evidence must be thicker to lift posterior odds significantly. A simple Bayesian setup for October: H0 equals natural background suffices. H1 equals measurable directed component exists. We list in advance observations strong enough to shift odds, such as a sequence of 3 to 4 windows in the month, showing strange rhythms not matching 24 hours or 27-day cycles, repeating within physical delay windows between L1 magnetopause ground, and coupled with durable spatial asymmetries not attributable to day-night geometry. Without enough points like this, posterior does not rise much, and that is the honest conclusion. Next is signal detection theory, SDT. In SDT, we care about sensitivity, D', and the decision criterion. With abundant plasma geomagnetic data, the biggest risk is tuning sensitivity too high and scooping up noise, or setting the bar too low and flagging every ripple. The remedy is blind test sets, mixed days with 3i Atlas active and without, weeks of high comet swarm and low, and time-shuffled upstream ground data packets. Group A sees upstream spectra, Group B sees ground PC5 and TEC. Group C sees comet morphology and astronomical calendar. Each independently marks anomalous rhythm by preset criteria. Only when markers overlap across groups within physical delay windows do we count as signal hit. This reduces false positives from internal consensus. Pre-registration is the lock. Before observing, we state clearly frequency band considered, e.g. 1.5 to 7 MHz for PC5. Delay windows, e.g. 30 to 90 minutes L1 to magnetopause, 10 to 40 minutes magnetopause to ground. Thresholds for thick background, e.g. PC5 energy above seasonal median by 1.5 standard deviations for at least 4 hours. And spatial asymmetry criteria, e.g. PC5 energy difference between adjacent latitude bands greater than or equal to 1 standard deviation for greater than or equal to 3 hours. Pre-registration also applies to communication phrasing, persistent background outlooks instead of alerts. When the campaign begins, we fill out forms like clinical trials. By month's end, the data speaks for itself. Multi-source triangulation ensures no single bird song proves spring. Upstream, beyond wave spectra, and BZ include thermal protons, alphas, and solar wind thermodynamics. Ground, beyond PC5, log surface electric fields and local resistivity changes, if networks exist. Ionosphere, beyond GNSSTEC, use HF sounders and incoherent scatter radars to catch plasma flows. Comet, beyond optics, use radio if ion tail signals can be detected. Triangulation also means model comparisons. Drive MSHD models with upstream conditions to generate predicted PC5. Only the unexplained residue is a candidate foreign signature. An effective side move is the statistics of absence. Over 3 weeks, if many windows show southward BZ and thick PC5 backgrounds, while 3i Atlas is quiet, yet the defined rhythm pattern still appears, H1 loses weight. Conversely, if such rhythms align tightly with Atlas's active phases and vanish when Atlas quiets even under favorable solar conditions, then H1 deserves more weight. Absent statistics force us to respect negative evidence, often ignored because it doesn't tell a story. Here, ethical and social questions enter. Suppose we detect some strange enough signatures. How to announce responsibly to the American public? The principle is not to personify nature. Directed must be framed as a test model, not as a character. Use probabilistic language. Posterior odds rose from 3% to 8%. Include confidence intervals and always pair with a natural rival model explaining 80 to 90% of data. Stress that community preparedness recommendations, emergency kits, family plans are independent of the hypothesis. For infrastructure, treat strange signatures, if any, as soft triggers for heightened monitoring, not red flags causing panic. We also need an open science waiting room. Instead of declaring big conclusions, open dashboards of processed data, source code, pre-registration forms and weekly reports. Invite independent teams to test again. A signature only truly lives if it survives critique. This culture matters because directed topics easily polarize believers and skeptics. Transparency is the only bridge allowing both sides to look at the same picture. Finally, we must keep the right to be disappointed. The highest probability scenario is H0 wins. Natural background explains most, with the rest in measurement noise or edge effects. Accepting that does not diminish the campaign's value. On the contrary, it upgrades operational standards. We gain better tools to describe background, more refined, persistent outlooks, infrastructure familiar with coordination rhythms, and a public treated like adults in a complex scientific story. Next time another stranger visits, the foundation is ready. 4 layers to test the directed hypothesis. Bayesian framework with low priors, raising posteriors only with strong repeated evidence. Signal detection theory with blind cross-group tests, requiring overlap of upstream ground comet markers within physical delay windows. Pre-registration of frequency bands, thresholds, delay windows, and spatial asymmetry criteria. Multi-source triangulation and MHD modeling to isolate the honestly unexplained remainder. Emphasize both positive and negative evidence. Use absence statistics and prioritize open data publication. I always recall a mentor's line: Good science is the ability to say not enough gracefully. Gracefully means with discipline, with transparency, with care for the listener. If October only shows us that the natural background is already rich enough to tell a compelling story, I will still be satisfied. And if a truly strange note does sound, I hope by then we have learned to hear it with the calmest ears. Part 11. Earthquakes as signals. Planetary response theory. The earthquakes as signals hypothesis begins from a simple yet bold shift of frame. Instead of viewing earthquakes only as mechanical outputs of plate structure and stress accumulation rates, let us treat them as one layer of Earth's system response to slow, broad, background stimuli arising from cosmic electromagnetic fields, as well as Earth's own endogenous rhythms. This does not deny the mechanical essence. It adds a modulation channel. Just as the heart beats mainly to its intrinsic pacemaker, yet still speeds up or slows down with hormones, breathing, or nervous state, faults also have their intrinsic rhythm from tectonic loading, but their triggering thresholds can be nudged by the overlying electromagnetic and hydro-atmospheric environment. To place this theory on scientific rails, we need a common language among seismology, rock electromagnetics, and space physics. Imagine a control block with 3 layers. The deep layer is the source, plates, fault geometry, imposed slip rates, and elastic memory. The middle layer is the modulation medium, crustal conductivity, pore systems and fluids, effective stress, natural and induced currents, atmospheric oceanic tides, and barometric pressure changes. The top layer is stimuli, solar wind, interplanetary magnetic configurations, PC5 oscillations, ionospheric magnetospheric currents, and slow variations of daily and seasonal cycles. Earthquakes are outputs of the deep layer, but the middle layer decides when micro-thresholds are exceeded. If the top layer supplies a structured, long-lived rhythm into the middle layer, the probability of a trigger pull in a loaded zone rises in a short window. One bridging mechanism between the top and the middle is induced currents and hydromechanical consequences. When PC5 backgrounds persist, currents in natural conduits, saline aquifers, conductive mineral belts, can increase slightly, altering zeta potentials on grain surfaces and thus modulating capillary pressure in pore fluids. The absolute change is small, but effective stress-controlling slip is sensitive to pore pressure variation in near-threshold zones. Such electrohydraulic resonance, if it exists, is spatially non-uniform, stronger where natural conduits and fluids are abundant. The response theory, therefore, predicts high locality, no global seismic wave, only pockets that hear the background better. Another mechanism acting as a phase tuner is slow slip and micro-seismic background. Many faults display slow slip episodes without radiated waves, lasting days to weeks, often accompanied by bursts of microquakes. If PC5 rhythms and ionospheric turbulence persist, ground electric fields can nudge clusters toward tighter spacing, shorter intervals between events, without changing total energy. This is the clock adjustment scenario. The system releases energy as expected, but distributed differently in time. To human eyes, it looks like more earthquakes, but in truth, it is clustered earthquakes. On a map, we can test response theory with 4 indicators. In conductive regions, saline sediment belts, graphite-bearing metamorphic zones, microquake clusters show increased temporal tightness when PC5 persists, even without high amplitude. In zones with histories of slow slip, the rate of microquake bursts rises within 24 to 72 hours after tech shows structured rhythms for many hours, holding weather-tide variables constant. A small portion of clusters spatially migrates along natural conductive pathways inferred from magnetotelluric surveys. Regionality. Effects appear on some segments but are absent on adjacent segments with different architecture, though exposed to the same plasma background. If these 4 indicators recur together, we have a strong case for earthquakes as responses, but still not a causal creation mechanism. The educational angle for American audiences lies in distinguishing trigger from cause. A relatable example is avalanches. Snow load, layer structure, and slope angle are causes. A sound or small vibration can trigger when slopes are primed, but cannot create avalanches on stable slopes. Likewise, tectonic load and fault geometry are the causes of earthquakes. Long electromagnetic backgrounds, if they play a role, are only the sound striking at the moment. The practical meaning of this distinction is large. It allows discussion of community preparedness without sowing fear and encourages investment in conductivity, maps, ground electric sensors, and denser seismic arrays. All useful whether or not the hypothesis stands. A strength of response theory is regional testability. If southern Alaska, northern Cascadia, and one San Andreas segment all share prolonged PC5, but only Alaska shows increased clustering, the logical conclusion is that Alaska's middle layer properties, conductivity, fluids, fit the mechanism better. This points to a new kind of map, plasma response sensitivity maps, alongside traditional seismic hazard maps. They do not replace earthquake forecasts. They only show where the background may be heard better. Yet response theory faces two traps. Trap 1 is the statistical which, in huge datasets, there will always be neat clusters coinciding with some PC5 background. The escape requires at least 3 repeats in one season, and controls are used during quiet seasons. Trap 2 is renaming noise as signal. When algorithms are too sensitive, every ripple becomes an indicator. The exit is pre-registered thresholds for clustering, tech rhythm, and replication by independent groups. At the societal level, treating earthquakes as signals can shift communication framing from forecasting, unfeasible, to favorable conditions. Feasible. A bulletin could say, in the next 48 hours, long electromagnetic backgrounds may persist. In zones with dense aftershocks, the probability of microquake clusters is slightly increased. No large earthquake alerts. Recommendation: continue standard preparedness, check emergency gear and communications. This preserves public trust while making plasma research practically useful, a layer of space geotech weather nested together. Earthquakes as signals sees earthquakes as mechanical outputs modulated by the middle environment, conductivity, fluids, pore pressure, under the influence of long electromagnetic backgrounds, PC5, induced currents, TEC variations. 2 bridging mechanisms: capillary pressure modulation via zeta potential from induced currents, and clock adjustment of microseismic slow slip under persistent PC5. 4 test indicators: tighter clustering in high conductivity zones, microquake bursts after tech rhythms, cluster migration along MT pathways, and clear regionality. All tests require quiet season controls and pre-registered thresholds. I do not see response theory as a golden key, but as a new pair of glasses. With them, I see the breathing rhythms of the system. Some places hear background more, some are deaf, but the main picture remains fault architecture and tectonic loading. Perhaps this is the best balance. Enough imagination to ask new questions, enough discipline to recall earthquakes, primarily because it is moving rock. The mindset here is no different from an industrial line. Inputs, pre-processing, modeling, testing, and finally public bulletins. Each step must be simplified enough for others to rerun and reach the same outcome within small margins. The first layer is the background clock. We need a summary number for long electromagnetic backgrounds every 6 to 12 hours for North America and the North Pacific, where seismic networks and infrastructure are densest. This could be a PC5 cumulative index by latitude, integrated 1.5 to 7 MHz energy at ground magnetometers, normalized to seasonal median, with persistence, consecutive hours greater than 1.5 standard deviations. Add a tech rhythm index from GNSS total electron content maps, autocorrelation strength at 20 to 90 minutes local time bands. Together, these two numbers show whether the background has pull and rhythm, necessary conditions for electrohydraulic coupling. The second layer is the conductivity lens. Without crustal resistivity maps, all pathway reasoning is blind. Magnetotelluric (MT) surveys exist sparsely along the US West Coast and Alaska. We must interpolate them into a 2 to 20 kilometer practical conductivity field depths of most microseismicity and slow slip. From this field, derive a conduit index for each 0.25 degree grid cell, depth-weighted mean log conductivity, and boundary contrast. High conduit index zones are where response theory predicts stronger sensitivity under the same P65 background. The third layer is the fault architecture clock. Not every day is equally near the threshold. Use seismic catalogs to estimate warmth of each segment, microquake rates, M1.5 to 3, aftershock accumulations over 7 to 14 days, and, if available, slow slip activity indices from GPS or tremor. Combine into a threshold thermometer from 0 to 1, where 1 means just had a major event/strong aftershock sequence, or at peak slow slip, when PC5 backgrounds sweep across regions with a high threshold thermometer and strong conduits. That is an ideal test case for response theory. The fourth layer is the clustering detector. Use standard seismological metrics, temporary changes in Omori-Otsu parameters for aftershocks, PC, modified, both statistics for size ratios, and especially clustering indices like Ripley's KT or Allen factor at minute-hour scales. Pre-register thresholds. Call a grid cell clustered if Allen factor greater than 1.2 in a 24-hour window with P less than 0.05 after diurnal seasonal controls. Importantly, run the same algorithm on quiet seasons, weeks with low plasma backgrounds, or inland low sensitivity regions to estimate false alarm rates. Now we can define a response candidate event. A day region where A. PC5 cumulative greater than 1.5 sigma for at least 6 consecutive hours. B. Tech rhythm passes threshold. C. Conduit index in top 30%. D. Threshold thermometer greater than or equal to 0.6. And E. Allen factor exceeds threshold within 48 hours after. Naming a candidate is not enough. We need repeats. Rule of 3. Only if the same fault segment shows greater than or equal to 3 candidates within 8 to 10 weeks do we conclude support for response theory at this region. Otherwise, 1 or 2 belong to random positives. 2 case examples illustrate. Case A. Eastern Aleutians after an M-score M7.0 last month. MT maps show a corridor of conductivity along the shelf. In week 2 of October, PC5 cumulative hit 2.1 sigma for 10 hours. Tech rhythm was clear at local dusk. Threshold thermometer 0.8 due to dense aftershocks. 36 hours later, a 15 to 22 kilometer deep microquake cluster burst with Allen factor 1.35, but no large event. Candidate recorded. Week 4. PC5 low, 0.7 sigma, thermometer dropped, no clustering. Week 1 of November. PC5 1.8 sigma for 8 hours, moderate tech rhythm, thermometer 0.65, clustering mildly up, AF 1.22, 2 of 3. If week 3 of November repeats, the chain meets the criteria. Case B, Central Cascadia, annual slow slip zone. MT shows good conduits, but October falls in a quiet slip phase, thermometer 0.3 to 0.4. Though PC5 twice exceeded 1.5 sigma, the clustering index did not pass the threshold. Provisional conclusion. Background is not enough when the system is not primed, consistent with response theory. Case B is a clear control, persuasive for the public. Background condition is not destiny. A practical obstacle is uneven data quality. Some Alaskan coastlines lack MT networks. Some magnetometers sit in industrial noise. Some remote seismic arrays miss small magnitudes. The solution? Quality triangulation, Include grid cells only if all three layers, magnetic, ionospheric, conductivity, seismic, meet minimal standards. Meanwhile, maintain a secondary data-adapted analysis to not discard sparse regions entirely, but keep them separate from the main conclusions. For public bulletins, the structure should be consistent, concise, and avoid confirmation bias. A favorable response condition bulletin could have 4 sentences. Today, PC5 oscillations were high for XY latitudes over Z hours. Tech Rhythm Index suggests a structured background. In segments with aftershocks slow slip, the microquake clustering probability is slightly elevated in the next 48 hours. No signs of major events. A 5th sentence gives infrastructure advice, GNSS, grids, as in earlier parts. This style deliberately demystifies, while letting readers feel they grasp long rhythms without fear. The final knot is statistical ethics. In a data and imagination-rich context, it is easy to polish low p-values. The antidote is reporting effect sizes and confidence intervals, preferring odds ratios over p-values alone. Example: odds of clustering increase 1.4 times, 95% confidence interval, 1.1 to 1.8. Within 48 hours after PC5, greater than or equal to 1.5 sigma and clear tech rhythm, with conduit index in top 30% and threshold greater than or equal to 0.6. Across 17 clusters/9 weeks in Region A dry numbers, but honest bridges between science and policy. Long term, a major side benefit of this framework is strengthening neural pathways among space, seismic, and infrastructure communities. Hotlines between space centers, grid ISOs, and USGS/NEIS, if they run smoothly for one season, become assets in facing a real G4 to G5 storm or complex aftershock sequences later. Even if response theory half survives, the operational legacy remains intact. Testing response theory requires 4 layers: background clock, PC5 cumulative and tech rhythm, conductivity lens, 2 to 20 kilometer resistivity fields interpolated from MT, summarized as conduit index, fault architecture clock, threshold thermometer from microseismicity, aftershocks, slow slip, and clustering detector, Allen factor, Ripley's K, Omori Utsu. A response candidate requires simultaneous convergence, high background, clear rhythm, strong conduits, high thresholds, clustering within 24 to 72 hours delays, repeated greater than or equal to 3 times per season. Public bulletins state favorable conditions, not warnings, and include effect sizes with confidence intervals. I like to see the whole process as orchestration: PC5 as strings, TECs as percussion, conductivity as room acoustics, and faults as instruments. When the ensemble is in tune, instruments resonate. When acoustics are good, tones are rich, but the music is still up to the musician. Scientific practice here is to prepare the acoustics and background rhythm carefully, then accept that sometimes the musician earth chooses silence, and that silence is an answer too. Part 12. Human meaning. Archetypes of destruction and renewal. There is always a layer of meaning running parallel to spectral curves. PC5, indices, or tech maps. The symbolic layer. Humans do not live only in electromagnetic and gravitational fields. We also inhabit a field of meaning, where the sky reflects collective inner stories. When an interstellar visitor, like 3I Atlas, appears during solar maximum, when Kamchatka shakes and auroras flare across northern US states, the collective mind pauses and asks, "What omen is this?" That question is not superstition. It is an ancient reflex, wired into how we detect patterns in chaos for survival. Science gives us tools to measure the background. Archetypes give us the vocabulary to speak of the emotions that surface when that background stirs. The archetype of destruction renewal is humanity's oldest symbolic cycle, from wildfires that regenerate vegetation to floods that leave fertile silt, to civilizations rising and falling, we gradually learned that some necessary breakdowns pave the way for new orders. In Earth science, faults accumulate energy and release it when thresholds break. Aftershocks are periods of stress reorganization. In space physics, the sun's magnetic field flips each cycle, rewiring the heliosphere's circuit. When an alien visitor arrives just as the circuit shifts, natural symbolism awakens. The new collides with the old, conductors spark, and arcs leap. Whether we interpret this through natural mechanisms or daring hypotheses, the sensation of standing at a threshold remains real. For American audiences, thresholds often come with anxiety. Recent history reminds us, every time the sky grows loud, a total solar eclipse, a strong geomagnetic storm, a rare meteor shower, social media erupts with apocalyptic predictions, conspiracies, and cascades of speculation. This is where archetypes quietly operate. Fear of the new, cloaked in celestial imagery. The best way to respond is not to dismiss symbols, but to place them properly. We can say, yes, this is a season of major shifts, solar maximum. Yes, there is a strange guest, 3i Atlas. Yes, tremors occur in sensitive regions. But change does not mean collapse. Strange guest does not mean invader. And tremors do not mean catastrophe. That shift reframes panic into attention, awareness, preparedness, and learning. Another useful archetype is the messenger. In Greek myth, Hermes moved between realms, carrying news from gods to mortals. In modern times, comets often serve as such messengers, not because they intend to say anything, but because their rare appearances lift human eyes to the sky, breaking daily routines. 3i Atlas, in this sense, reminds us that the solar system is not a sealed box. It breathes with the galaxy. Seen as a messenger, the focus shifts from what will it do to us to do we have the ears, instruments, and mindset to listen and measure. This frame preserves poetry while pressing us to improve measurement and data coordination, a graceful link between symbol and action. At the individual level, each viewer enters a small personal solar maximum when consuming dense news, spectacular images, and colorful theories. Our nervous system, literally electrical, is rhythm sensitive, favors coherent storytelling, and easily locks onto repeating patterns. When feeds repeat omen, mystery, destiny, the brain grants us a sense of order even if false. The hard but valuable practice is designing a personal PC5 filter for mental life. Some days, lower the rhythm, reduce the amplitude of stimulation, let the nervous system reset, then return. This is not avoiding reality, but cognitive hygiene to face reality more clearly. On the community level, the archetype of destruction renewal can be guided positively, turning the plasma season into an education season. Libraries, schools, and local stations can co-host plasma nights, watching auroras via live stream, learning about solar wind, discussing grid protection, and sharing family emergency plans practices that outlast noisy moments. Instead of debating directed energy or conspiracies, communities practice renewal archetypes, cleaning storage, updating emergency kits, checking backup batteries, and, most importantly, learning to talk in crisis without falling into believe-don't believe binaries. Another archetype slips in, map and territory. In our story, maps are spectra, indices, models. Territory is the sky and the trembling ground. Humans confuse the two. When maps grow detailed, we think we own the territory. But maps are compressed stories. They are useful because they compress, but because they compress, they omit. Reminding ourselves of this keeps humility before data, admitting that microquake clustering may have causes not yet measured, that an odd ion tailbend may be geometry, not a new mechanism, that spectacular coincidences still have the right to be coincidences. This humility does not diminish us. It elevates us, keeping the dialogue between map and territory open. In policy life, the archetype of collective responsibility finds its place. Strong solar storms are chances for federal, state, and local agencies to rehearse civic rituals for disasters, official channels, rumor verification protocols, and hotlines. As 3i Atlas passes, we can borrow public curiosity for mini drills. Such drills both respect the public's intelligence, they want to understand, and can understand and build immunity against misinformation floods whenever skies turn strange. Close this section with an image. Imagine a choir, the sun as bass, earth as alto, 3i's Atlas as a soprano sweeping above. When the soprano rises, we notice harmonies are always present but faint. That is the gift of the strange visitor, not its high note, but its power to let us hear our own background more deeply. Having listened, we return to daily life, with power cables, GPS, and family dinners, and tend them with new knowledge, calm, and love for a planet running rhythms larger than all of us combined. The archetypes of destruction, renewal, and messenger place celestial seismic phenomena into frames of meaning without panic. Using symbols correctly shifts omens into background conditions and apocalypse warnings into education and preparedness. 3 practical principles. Acknowledge big rhythms, solar maximum, without personifying them. Design personal rhythm filters for nervous systems, and turn communal curiosity into preparedness practice. Always distinguish maps, indices, models from territory, nature. Keep humility before data and coincidences. I now believe the best science does not kill wonder. It trims illusions so wonder appears in true form. Seeing 3i Atlas as messenger and Kamchatka as reordering rhythm, I glimpse sky and ground stitched by a thread both real and poetic. That thread takes me back to my desk, to data, and at the same time nudges me to call family about their emergency kits. Between those acts, I feel myself a better citizen of this planet. We begin from reality. Digital infrastructure delivers space weather, aurora, or Kamchatka aftershock news to you in seconds. The brain thus stays in alert mode longer than naturally. Without ritual transformation, attention energy disperses into panic, arguments, or fatigue. So what is the minimal ritual? Ritual 1. Naming and framing. Whenever news clusters geomagnetic storm, aurora, 3 Atlas, earthquake, silently call it plasma background season. Framing gathers fragments into one story. Sun at maximum, interstellar visitor passing, electromagnetic background rising, infrastructure and natural systems responding by built-in sensitivities. Naming shifts the brain from omen to condition, easing panic. Local media can standardize this as simple graphics, like weather forecasts for UV or pollen indices. Ritual 2. Dialogue across worldviews. US audiences are diverse. Some purely scientific, some spiritual, some UFO enthusiasts, some tuning into local news for tomorrow's rain. Instead of exclusion, design conversations where each gets a shared mold. That mold has 3 layers. Data, KP, PC5, tech, Quake catalogs. Scientific interpretation, with gentle triggers, long background, and meaning, seasonal archetypes, messenger. Scientists hold the data. Spiritualists offer meaning, but are reminded not to personify nature. Mystery lovers are encouraged to ask good questions, then test them with blind checks. With roles clear, conversations grow rich, not chaotic. Ritual 3. Channel curiosity into skills. Aurora season is a chance to learn storm maps, data protection, and backup power checks. Aftershock season is the time to review food, water, medicine, flashlight supplies, and draw family contact plans when networks fail. Many US cities already run Emergency Preparedness Month. Weave plasma nights into those calendars. Children can do small experiments, coil, magnet, LED bulb to grasp induction. Adults can learn to toggle GNSS ionospheric models for farming. Curiosity is the best fuel for discipline. Ritual 4. Slowing down. Paradoxical in a dense season, but human perception cannot stay lit too long. Choose an evening to mute notifications, step outside if safe, and look at the sky instead of feeds. If nothing unusual appears, good. Sky's normality is an anchor. Return inside. Write 5 lines of what you learnt that week. I learnt to read KP Index. I know auroras can reach Montana. I installed USGS alert apps. Simple journals ease the fear of missing out and preserve personal science memory. Ritual 5. Practice kind language online. Misinformation spikes every season. Plasma season more so. Train a reflex. When sharing aurora photos or storm maps, attach a clear source and note, background condition, not disaster forecast. When someone calls 3i Atlas a mothership or weapon, don't scold. Ask, what measurable signature would differ from natural? Assign them to proposed tests. The right questions cool debates. If overloaded, retreat gracefully. I'll return after checking data. At the civic policy level, use this season to build bridges between agencies and people. NOAA, UGSG, and NAS. All run real-time dashboards. A unified portal at the state or city level named playfully Sky and Ground Today could combine KP, Ground PC5, TEC maps, local aftershock lists, and infrastructure tips, not to predict quakes, but to remind everyone of favourable conditions and repeat preparedness advice. When people know where to look for one map, panic contagion drops sharply. Finally, healing. Not all meet plasma season as intellectual play. For some, red skies, storm alerts, and quake clips revive trauma memories. They need gentle words. You may turn off. You may not watch. You may only prepare the basics and leave the rest to scientists. Religious or community groups can host hours of peace alongside plasma nights. Not prayer instead of science, but prayer and science both serving one aim, keeping hearts steady as sky and ground shift rhythm. One final image. At its purest, 3i Atlas is a call to see beyond 9-5 loops. It reminds us we live in an electromagnetic machine so intricate and beautiful that even physicists often exclaim, "Marvelous." When we feel that beauty, we usually treat each other more gently, because between storms and aftershocks, the most fragile thing is not the grid or GPS, but trust between people. If that bridge holds, every plasma season becomes a season of growth. 5 rituals for transforming celestial seismic seasons. 1. Name the plasma background season to frame scattered news. 2. Layered dialogue between data science meaning, avoiding personification. 3. Channel curiosity into infrastructure and preparedness skills. 4. Practice slowing and journaling to ease overload. 5. Discipline online language with test questions and clear sourcing. At the system level, build a Sky and Ground Today portal, merging KP, PC, 5, TEC, aftershocks, and advice. I once thought meaning was the enemy of data. The more I work, the more I see the reverse. When meaning is placed rightly as frame, not conclusion, it helps data settle in minds. I want 3i's Atlas to pass over America as a festival of understanding. More people learn a skill, more homes are prepared, more conversations grow gentler. If that happens, no matter what the gentle trigger theory yields, we still win. Part 13. Consequences. Technology, society, and consciousness. If the entire journey so far has given us a multi-layered picture of 3i Atlas, the solar maximum, and long-term background rhythms, then this part goes straight to the question, so what? On 3 levels: technology, socio-economics, and consciousness. A season of plasma background is not only about beautiful aurora images or flickering PC5 charts. It is a stress test for the systems America relies on every day. The difference between an interesting anecdote and a good policy lies in how we can turn physical knowledge into technical procedures and community habits. On the technological level, the three most sensitive fields are the power grid, positioning, navigation, timing, PNT, with GPS at its core, and satellite telecommunication infrastructure. The federal grid and regional ISOs are used to peak geomagnetic storms, but it is precisely the long background that causes lingering fatigue. Induced ground currents smoldering for hours can push old transformers into higher loss zones, overheating insulating oil beyond thresholds without a clear event peak to trigger protection. The operational lesson is to set background thresholds alongside peak thresholds. If PC5 accumulates at a latitude band exceeding 1.5 to 2 sigma above the seasonal median for more than 6 to 8 hours, operators can proactively shift loads, increase thermal monitoring, and reduce heavy maintenance in the sensitive window. This is not a panic alert, but a discipline to preserve safety margins. With PNT, the issue is not only instantaneous position error, but time noise seeping into synchronization chains for finance, power grids, and 5G networks. When the ionosphere is disturbed by long background rhythms, standard ionospheric correction models may lag, causing time jitter at synchronization stations to rise. The service-side solution is to switch into an ionospheric-aware mode, increase update frequency of models, consider multi-constellation, GPS Plus, Galileo Plus, Beidou, and most importantly, strengthen PTP/IEE1588 internally as a backup when sky signals degrade. For large users like precision agriculture or construction, a simple, long background notice is enough to shift sensitive work into calmer hours, saving thousands of dollars in errors. Satellite and telecom infrastructure face the problem of long drizzle soaking through clothes. Slightly elevated radiation doses lasting many days can raise bit error rates, forcing error correction systems to work harder, reducing real throughput without anyone naming the cause. For low Earth orbit, LEO, changes in upper atmosphere density due to mild but prolonged geomagnetic activity can increase drag, requiring earlier orbit adjustments than planned. Operators should embed background filters into task schedules, allocate wider margins for downlinks during high background sessions, check electronic temperatures more frequently, and prepare temporary gear shifting protocols for satellite constellations passing through sensitive latitudes. These are the new normal when a solar maximum coincides with an interstellar visitor, which makes us observe more closely. Socioeconomics receive a different kind of aftershock, information aftershocks. A media ecosystem driven by spectacular images will amplify cycles of attention, confusion, fatigue. Small businesses may be drawn into panic, planning by rumors like GPS will shut down, and schools may cancel outdoor activities based on color maps without explanation. Thus, a background condition bulletin should become a public service like weather forecasting, with two key features: risks zoned by latitude, infrastructure, and probabilistic language. A simple ticker on local TV. Space ground background, moderately high today in the Midwest. GNSS may see minor interference. No impact on flight safety, few words, but enough to bridge physics and daily life. On the micro level, society experiences a kind of electric rain falling into the mind. The new rhythm activates old patterns, conspiracy theories, science-spirituality divides, arguments about meaning. The most effective way to vaccinate consciousness is not to deny emotions, but to provide tools to read the world. When an ordinary American knows how to open a dashboard, sees how KP approximately 6 differs from KP approximately 3, understands what long PC5 means, and trusts that if there is something truly worrying, government and local stations will speak in plain words, then the energy of argument turns into the energy of learning. Children are drawn into school projects, measuring the sky. Adults hang a small checklist next to the family emergency kit. What to do during a geomagnetic storm. Finally, Consciousness. A season like this is an invitation to broaden our sense of perception. Instead of looking at the sky as a backdrop, we see it as a continuous flow of energy in which Earth swims. This perception has two opposite but healthy effects. It makes us smaller, humble before larger rhythms, and it makes us larger when we see ourselves as responsible parts of a fragile system. The shrinking experience helps reduce anthropocentrism. The growing experience awakens an ethic of care for infrastructure, for community, for truth. Speaking of truth, one of the most valuable legacies of this season may be the habit of reporting even when nothing happens. That culture sharpens trust. When citizens see bulletins repeatedly say, "Background high, but nothing to worry about. Still check backup batteries," and it turns out exactly that way, they learn to live with the new rhythm without emotional dislocation. Trust is not born in great storms. It accumulates in long background days when everyone does their small part right. The practical consequences of long background concentrate on three infrastructures: power grids, prolonged induced currents, need background, thresholds, and proactive load shifting, PNT/GNSS, ionospheric disturbance, need ionospheric aware mode, multi-constellation, internal time backups, and satellites telecom, slight bit error increase, LEO drag, need margins, and adaptive schedules. At the social level, deploy zoned probabilistic background condition bulletins. At the individual level, provide minimal dashboards and checklists for what to do in a geomagnetic storm. Consciousness is nurtured by the shrinking growing perception simultaneously. I have done science long enough to know that the most lasting changes rarely come from one sensational discovery, but from a new habit that spreads. If 3 Atlas and this solar maximum season help America develop the habit of reading space background bulletins, checking backup batteries every quarter, and speaking to each other in plain words during high background days, I think that is a rare victory where physics, policy, and the human heart meet. The rest of the consequences lie in specific decisions at the policy, research, and social equity levels. A season of long background is a rare opportunity to practice risk governance when information comes from many different frames of reference. We need a roadmap both humble before uncertainty and proactive in what we can control. At the policy level, the most practical step is to recognize space weather as a daily forecast layer equal to rain and sun. This does not mean every city needs its own space center. It means local emergency departments have a standard process to receive, understand, and broadcast background condition bulletins in coordination with local stations. The bulletin states briefly the day's conditions, affected regions, possible impacts on power and navigation, and especially what will not happen. Emphasizing what will not happen is an important technique to reduce speculation. Each state can appoint one liaison responsible for this bulletin layer. Training procedures, as with winter storms or wildfires. At the research level, a 3-year interdisciplinary program could make a big difference. Axis 1 is open real-time data for ground, PC5, TEC, and surface electric field indices with quality maps so non-experts can understand limits. Axis 2 is research on electromagnetic, hydromechanical coupling in real rocks, not just simulations. Lab experiments with fluid-saturated rock samples placed under long oscillating EM fields, directly measuring capillary pressure changes and slip thresholds. Axis 3 is operational modeling for infrastructure, where space background data are incorporated into load shifting, maintenance schedules, and timing synchronization configurations. These 3 axes converge on the common goal of making plasma background a condition variable in decision models rather than a vague unknown. One often overlooked but essential branch is data governance and language. Words like geomagnetic storm, radiation, and interstellar can easily be turned into clickbait. Agencies could release a pocket encyclopedia for the long background season at a popular level, with each entry with a short definition, everyday impacts, and notes on what is unknown. This serves as a shared standard, a reference so the press and social media don't drift too far. Alongside it, a set of template phrases for background bulletins standardizes probability usage, time ranges, and action recommendations, helping avoid confusing variations. Social equity is an indispensable plane. The impact of space weather does not fall evenly. High-latitude communities face a greater risk of power outages. Farmers and fishers more dependent on GNSS are more sensitive. Rural schools have a thinner tech infrastructure to adapt when the internet falters. Therefore, every adaptation plan should have a small but clear budget line for vulnerable communities. For example, support backup charges for households in cold regions, mobile data subsidies for teachers when online classes are disrupted, or funding installation of internal timing synchronization for small businesses relying on real-time payments. Small investments have large effects as cushions against background oscillations. Mental health is a soft but deep consequence. Waves of news about geomagnetic storms, auroras, and aftershocks leave many people living with prolonged unease. We can learn to tell stories without draining society's emotional reserves. One method is the two-beat model. Beat 1, announce background status, emphasize normality, give compact recommendations. Beat 2, when something truly unusual occurs, trigger a warning modal with clear wording, no ambiguity, helplines and verification sources. Everything in between, including beautiful images, goes into the educational curiosity channel, not the operational channel. This information design is like painting priority lanes for ambulances in rush hour. Culture and art play roles in transforming collective experience. Community aurora, nights in parks, photo exhibitions on the sun, light art projects, simulating PC5 rhythms, school documentaries on electricity and the sky, all turn a potentially anxious season into a season of looking up and learning together. The scientific community can actively partner with science museums, theatres, and artists to tell the plasma background story through images and sounds, turning dry data into a tangible experience. When beauty enters, fear retreats. At the business level, the lesson is adding another layer of rhythm management. Telecom companies define background thresholds for error counters. Finance companies define time jitter thresholds for trading systems. And precision agriculture companies define TEC thresholds for planting schedules. Set thresholds, write playbooks, run drills. Don't wait for a federal notice to act, because what is needed is smooth internal rhythms. This season is a free, practical course to fine-tune rhythms. The further vision of the consequence layer is laying the foundations for a civilization that knows how to live with sky rhythms. That sounds lofty, but it begins with small things. A dashboard opened every morning, a background bulletin added to the broadcast schedule, a PC5 number appearing alongside pollen counts, an emergency kit with backup batteries and a contact list, a STEM class for kids about solar wind, a grid ISO meeting with an added background data field in decision charts. Piece by piece, over time, they form collective maturity. We cannot control when an interstellar visitor appears, nor decide when a fault slips. But we can control how we prepare, how we speak, and how we care for each other. If from 3i Atlas and this solar maximum emerges an ecosystem of habits like that, then that is the most lasting consequence. Next time, whether the sky has many strange visitors or not, we will already have eyes trained to see, ears trained to hear, and a heart less panicked before the great rhythms of the universe. Pragmatic policy for long background seasons consists of 3 pillars: recognizing space weather as a daily forecast layer with standard procedures at emergency departments, a 3-year interdisciplinary research program connecting open data, EM hydromechanical lab experiments, and infrastructure operational modeling, a dictionary and template phrases for background bulletins to unify language. Social equity requires a small budget line for vulnerable communities. Mental health is protected through the two-beat information model. Businesses adopt rhythm management and playbooks by background thresholds. I think the most beautiful consequence of such a season does not lie in any graph, but in how an ordinary city adds to its ordinary habits one new detail. Every morning, looking at the sky, looking at the ground, and asking each other a very simple question: how is the background today? That question, repeated through the years, transforms a reactive society into a responsive one. Part 14. Earth as a laboratory in the universe. From Kamchatka to the auroral oval, from the long PC5 rhythms to the ion tail of 3I Atlas, this journey has carried us through two parallel worlds: the world of measurable natural mechanisms and the world of open questions where imagination forces us to raise our standards of verification. We have looked at earthquakes as mechanical outputs modulated by the electromagnetic environment, posed hypotheses about energy harvesting as rigorous thought experiments, and translated all of that into practical habits for infrastructure, communities, and individual households. Whether 3I Atlas is merely an interstellar visitor or a vast plasma antenna, perhaps the greatest value it brings is opportunity. The opportunity to measure backgrounds more precisely, to collaborate more deeply across disciplines, and to learn how to live with the rhythms of the sky without losing composure. Earth, in its most beautiful sense, is a laboratory in motion within the universe. Here, we do not only track waves and numbers, we also learn how to tell honest stories, respect what remains unknown, and care for each other during the long background days. If there is one message to carry forward after this episode, it is the spirit of responsiveness. Measure before believing, prepare before worrying, and share before judging. Thank you for joining us. If you found value in this, please subscribe, turn on the bell so you won't miss the upcoming chapters, and leave a comment about what you'd like us to test during this solar maximum season. Every one of your questions is a small experiment that helps the great laboratory called Earth work a little better.